Okay. Assalamu alaikum. Uh, Today, inshallah, we will have another talk or another lecture. Inshallah, we will talk about physical characterization of heterogeneous catalysis. Actually, as I just mentioned, it is the most important part in your work because it gives you a chance to know what is the material you are treating with, and if you are going well and already prepared the desired material or not, and the material which is in your reaction is the same as you want and uh, make the suitable or the expected or the desired mechanism or not. Okay, let's start to not waste our time. This is a physical characterization. Of course, you know that several techniques are used in this purpose, which is the characterization of heterogeneous catalysis. Not only heterogeneous catalysis, but characterization of materials, because these tools also are used for characterization of other materials in geography or in geology or materials in medicine or something like this. Not only heterogeneous catalysis. The same tools are used there as well. Okay. What is the main principle of these tools? All of it, of course, they are divided into several basics like thermal techniques, like for example BET or TBD and TBO and TBS and so on. This is thermal techniques, or DTA, TGA. These are thermal techniques. It depends on heating the material, and maybe spectroscopic techniques like X-ray, IR, XPS, and so on. Every or UV, every tool depends on your effect on these materials with an effect like temperature or like light, whatever the light is. It may be infrared, it may be UV, it may be X-ray, it may be something. And you detect what is the effect of your effect on these materials. Okay? That means you detect the feedback of your effect on these materials. Several spectroscopic, microscopic, these are this is radiation of a catalyst with X-ray, for example. Photons generates and photoelectrons which are employed in X-ray and XPS and something. This means that you detect the effect if you feel, if you find this is catalyst, and you may affect on this catalyst with several effects. After that, you detect the effect or detect the feedback from these effects. Let's have, of course, I'd like to remind you about these effects may change in time, change in scale of the material size, change in scale of how much heat you need to do, a change in scale of how much pressure you need to do. For example, some in pressure, some techniques needs vacuum, meets high ultra vacuum medium. This means nothing at all on the sample. Okay, on your sample. Others need or don't mind if there is real conditions there, like this sample is in air or has some absorption on this, and so on. And others may need very high temperature, and like TBD, or as I just mentioned, those tools depend on the temperature, like TBD or DTA and something. And others need may detect the material in very small particle size in nanometer scale, 1 nanometer, 3 nanometers, and this scale. And others may detect the material or can check the material in large particle size in micrometer scale. These are, you may use ultra high vacuum or very high pressure, or some methods use in liquid nitrogen temperature, which is very low temperature, and the others use very high temperature. And some methods use like in you detect, you try to detect the conditions and the material in the real conditions. Like if you want to make an experiment for the purification of water, so you have to go to some place which has wastewater, like in the cereal field. So you bring real, which is waste real water, to make your experiment. This is the real thing. But if you want to imitate, you can just check the degradation of dyes in water or something. This is not the real thing. Just imitating the real conditions. We have some methods. I will try to explain some of these methods which are used in the characterization. We have traditional methods, like there are two types of absorption. Of course, we just checked yesterday, and we will depend on this physical absorption or chemical absorption in some of our, not our, in some of the used techniques in characterization. Let's see how it will be. Number one, only I'd like to remind you about this. Number one is that determining the surface area and the surface texture. This is one of the traditional techniques used for the characterization of the catalyst. This is very important to know how much is the surface area of the catalyst and what are the surface properties that you have, like surface area or external surface area, internal surface area, micropores volume, or even the aperture or the opening of the pores, how much it is, because it will be benefit for you or beneficial for you to know what kind of material for selectivity it can be used, as we will mention later on, inshallah. This technique you can measure surface area, the volume of by detecting the volume. If you remember yesterday, we mentioned about monolayer volume of gas, which covers all the surface. If you measure this, you can easily measure the surface area of your material. I think we explained yesterday. Okay. This technique measures the monolayer volume, and also this is, of course, this is chemical absorption, and also it makes a kind of physical absorption to measure other parameters, like, as I mentioned, pore volume, mixed condensation, and so on, mixed condensation in the pores, and so on. It makes isotherm. Of course, I'd like to remind you about what's isotherm. Isotherm is you measure something at constant temperature. You measure something at constant temperature. So you measure absorption at constant temperature. Okay, that's what will we will be explained just now. This is the old technique, not old technique. This is the old system that we were used. I myself used something like this. This is the old system that uses was used for the detection or measurement of surface area. If you can see, I will not explain the system, but only the part of the sample. This part of the sample has two cells. Okay, one is a reference, and the other one is containing one our sample. Okay, and we heat it by a heater. Just add a heater in the same like the same way. We add a heater and heat it to evacuate the surface. After evacuation of the surface, after it's being clean, now no gas at all, we add our gas, which is nitrogen adsorption, make nitrogen adsorption. After adding the nitrogen, we just take how much nitrogen it is absorbed, and then we plot the absorption curve. After that, we make evacuation and measure how much gas is evacuated and make a desorption curve. From absorption and desorption curve and its shape, we determine the exact shape of the, but with, of course, with some calculations, not only with the shape. Some calculations, we determine all the texture parameters. And this is the, okay, this is the new, this is the new, this is a new technique or new instrument that is used for the for BET. And of course, this is not the only one. There are several shapes of this instrument, several shapes, because each instrument you will see in your life will, its shape will depend on the company which will produce this instrument. Okay, let's skip this. Of course, these are other shapes, and this is what we are talking about. These are the absorption isotherms. These are the only, it was 5, and they recently added a 6th one. This is the only 6 shapes for absorption isotherm, as absorption isotherm. The first one, second one, third, fourth, fifth, each one of these makes indicate a character or the properties of the surface. Let's check one by one. Type 1 isotherm, of course, this indicates a Langmuir adsorption. Langmuir adsorption, because it is talking about only monolayer adsorption. Monolayer adsorption. So monolayer, of course, directly your mind should go to chemical absorption and Langmuir isotherm. This point, this black point there, indicates that saturation of monolayer has gone, is obtained. This is type 2. After saturation of monolayer, the volume, absorbed volume, the y-axis is the absorbed volume. X-axis is the pressure, is the applied pressure. Increasing this curve means the absorption increases, the amount absorbed increases. This means if the amount the amount absorbed of nitrogen increases after monolayer, this means we still have chemical absorption, or we change it to physical absorption. Condensation of the gas will happen, and the absorbed amount will increase like this. Of course, there are other shapes like this shape, type 3 and the type 5. Both are physical absorption. And type type 5 is like this. Of course, it combines physical absorption and some parabola up there. This is type 4 is different, and this is the most important part in catalysis, because most of the catalysts which have pores have this type of isotherm. This is an example of the data you can obtain from. This is our data in one publication. As you can see here, you can find the first column. The first column on the left. These are the samples we used. The second column explains how much is the total surface area you have. The second one is the theoretical surface area. The next one is microporous volume or surface area. The other one is mesoporous because you can measure microporous volume and mesoporous, and the external, this is external surface area. So if you subtract external from internal, you will find that internal surface area is very huge. Pore volume, the pore volume, and if it is micropore and or mesoporous material. And what is R? R is the radius of the opening of cavity or channel, and this is C constant. It is very important to determine the nature of your material. And this is microporosity. How much is it? All of this data you can determine from these isotherms. After some calculations, there is another T plot you can also obtain from these isotherms. I think we just gave you a general idea about surface area measurements and what you can get and what you can do with this technique. The other technique, which is also a very important technique, that you will use to see and detect what is the surface composition of your material. If it has acidic sites or basic sites, or even if these basic or acidic sites are strong or weak, and what is the type of linkage between these sites, you will see here. This is TB. TB means temperature programmed techniques. Temperature programmed techniques, you can, this is an expression. You can add a third word to this expression according to the technique you will use. It may be, of course, this is a technique measures the reactivity of a solid as a function of the temperature under controlled conditions, of course, and the temperature at which species react on the surface or indeed are desorbed from it, because the temperature of adsorption or desorption determines how strong your site is, if it is a strong acidic site or strong basic or weak, or because the temperature, if it is high temperature of desorption, for example, this means it's strong acidic site or basic site, and vice versa. Of course, we have different techniques from this TB, which are as I mentioned. But if you change the absorption, you will have different data from each and have more information. The more reactive species react at lower temperature, and vice versa. Of course, it is more reactive species react at lower temperature. But if this is if you make adsorption, and vice versa, if you make desorption, then the more reactive species will desorb it at higher temperature. The most common TB techniques are temperature programmed desorption, temperature programmed reduction, temperature programmed sulfiding, or temperature programmed oxidation. Those are the most important ones, and I think you can't find the others. Of course, it is depend on the functional group and the absorption. Let me show you something. Also, it is realistic. It means that you add some adsorbent or some gases on the surface, and it measures the effect of desorption. This at the presence of gases, it is realistic. Yes, you can monitor the changes that the catalyst precursor goes through during the calcination and activation steps. Let's check something here. Sorry, this is repeated again. This is the technique of temperature program. I think you can see here that this sample, in this sample, I will not explain all of this because these are just valves and reservoirs of gases and a sample holder. This sample holder, we just make heating and to evacuate the sample and make it very clean from all gases, and then add I'm sure you know nitrogen, liquid nitrogen trap, and not liquid nitrogen. It's a reservoir of liquid nitrogen just added here to make absorption at very low temperature. Then evacuate and measure the output of the gases. In this case, this depends on GC very much, because how come it depends on GC? Because it measures the amount or the intensity of the gas that enters to the sample, and measures the conductivity or the amount of the gas after going out of the sample, and it measures how much the sample took from this in this case. This is a very simple. No, this is modern one for this characterization, and in this case, it has many of the types of TBD, TBR, TBO analyzer. It has all. Just you click and you can make it as you want according to the gas you add to this instrument. Uh, this is a simple diagram, shows how it works. Of course, reactant gas you input in this the gray cylinder is the reactor, or it's the place of the heater. It's around it, okay? And this is catalyst sample. The gas goes to the catalyst sample, make absorption. After, and of course, we control the temperature at this time. And then thermal, you measure the gas after going out from the sample like this by mass spectrometer or by any technique, or by GC. This is and this is the data you can get it from like this. These are three samples. The first one is copper oxide. The second one is cerium oxide. The third one is a mixture of copper oxide and cerium oxide. I think you can easily distinguish the difference between the three samples. The first one is copper oxide, has a peak around 200 degrees C, but adding cerium, it shifts this peak to lower. That means that it made the acidic side is or basic side is little bit weaker one. After that, there is a difference in higher range of temperature as well. You can check here the effect. Also, I have something to tell you, that you don't invent science. I mean, you always depend on previous people data. I mean, you before going uh, to any experiment, you have to check what the other people did before you go to this experiment. I mean, this is literature review about what you want to do. Just check what the other people did before you, and what they already said, to just to continue after their knowledge, to build your knowledge on their knowledge. That means which they say that before 200 it means something, and after 200 or after 600 it means other thing. You are taking this information from your in your consideration, and build on this. Another advice you have to take it: don't take anybody's data as trusted data. Okay? No, sorry. Don't take any data from any literature. I mean, you just rely on trusted data. Also, I want to say that you don't rely on the other people interpretation, which is because I can see this data. I have a point of view or understanding or realizing or understanding this data. It's my point of view. It's according to my understanding and what I get and what I add new data, and so I explain this data. You may explain this if you see this data, and you may explain it better than me. You may have a better knowledge or better understanding for this data than me, even if it's my data. If it's my data, yes, but uh, anyone can understand it better than me. Somebody may understand it better than me. Okay, so don't rely totally or completely or on what I said. Criticize what I said sometimes. That's why some schools make a kind of review seminars, not regular seminars. They say it review seminars means I try to find a topic and search the previous literatures about this topic, maybe 10 articles. I add these articles and criticize, not criticize, understand the data without what the people or those people said about their data. For example, this is a type of our data. I will show you. Uh, of course, this is what I already mentioned about the data. These are my data, okay? But you may understand it better than me if you read and try to understand it. This what I did here. I added carbon monoxide plus oxygen in equal ratio to make simply to make CO2 as a product. Okay. Of course, people are trying to oxidize CO because CO is much harmful than CO2. On two samples which are platinum on Y-zeolite and platinum iron on Y-zeolite as a mixture of metals. I just added CO plus O2. At this time, I got peak at 141, maybe 140 for platinum iron. In the same time, only one peak for platinum Y was obtained very high, over 440, 50, sorry. So I checked the literature. I found that they classified or make it three zones. The first one is low viscosity sites where CO2 was dissolved below 150. This is CO2, okay? If it's CO, it will be in another region, in another place. And this is medium sites, which around 400, and high or very high viscosity sites, which are above 400. This means that this site or this surface has basic sites. We of course we didn't expect it, but it is basic. There are basic sites. Of course, we have other things we can mention here, but of course, I want to go to a very important technique that you will daily use. This technique is like TBD or surface area. You may not use it so frequently, but for XRD you will daily use it. Why will you use it daily, not daily? Daily, because it shows you or it informs you about the structure of the material you have. It gives you several informations. The first one is basically if your material is amorphous or crystalline. The second purpose is what if it's crystalline. If it's amorphous, of course you will full stop and leave this technique. That's it. If it's crystalline, you go to next step. What is the crystal? Just look at it and find the crystal structure. No, there are some cards previous people or very high or trusted organizations has some cards. It shows you this peak for this material, which has, for example, copper oxide. It has copper and oxygen. The material which has copper oxide may be number one, copper 2O. Sorry, copper 2, yes, copper 2O. Or copper O, or something. This means that if it's Cu2O, this means it will give you peaks somewhere. And these peaks will have some characters, something. And if it is copper O, it will give you other peaks somewhere, and so on. Okay, let's check. So number one, if it's crystalline or not. Number two, what is the structure of this crystal? Number three, what are the d spaces or lattice parameters of this material? Number four, what are the crystallinity? And number five, it may give you the crystalline size by something or some equation which is called Scherer equation. It gives you crystalline size. Let me check with you. This is an old version of X-ray, and this is a new version of X-ray, and this is newer version of X-ray, which it has also bench top X-ray in this size or this size. Bench top means you can just move it from here and there. The others, it is only will be fixed in a room, an entire room. And this is very small, and the geologists are using because they can move it. And before going to spectra, this is a spectrum of radio waves, microwaves, infrared, visible, ultraviolet, X-ray. Of course, these two X-ray is one of the highest frequency or lower wavelengths techniques. So it is very dangerous. Basically, it is like this. Of course, this is the main idea. On the left hand, this is X-ray tube. This is the source of X-ray, and in the middle, this is the sample, and on the right there is a detector. That's it. Rotation occurs to change the angle of incidence, and this detector will record the data given. Of course, I'll not go deep in this technique, but I mean in this point, but we will understand more about it. This is the X-ray, and of course, these are the reasons why we use X-ray. And this is Bragg equation. This is whenever you study X-ray, you will find this equation. Whenever you want to know something about X-ray, you have to go to this equation. This is D. In this equation, it can determine the D value. D, which is D spacing, is the distance between two lattice planes. Of course, I'll show you what are the distance of lattice planes. This is the distance of lattice planes. This is the layer, first layer. Of course, this is what we just mentioned in previous studies. This is a source. It goes to the sample, and of course, rotation. This rotates from here and like this, like this, like this, and this is reflected to the detector here. These are planes. This is the first plane, second plane, and so on. Of course, this is incidence or X-ray. This goes to the first plane, and this goes to the second plane. And they are reflected here and detected without your work. But new instruments calculate it. But only I'll just give you what is its idea. The height, you measure the height because you may need it someday. You measure the height, divide this height by 2 to go to the half width, and measure this half width and transform it into radian values. and then you can apply in this equation and determine the D, which is not particle, crystalline size. Now I think uh, we just introduced a simple idea about XRD. Now we will go to another technique which depends on light as well. No, which depends on another thing, which is electrons. This is electron microscope. Actually, I just told you that XRD is the most important technique that you will use daily in your work. TEM may be the same or next one. Why? Because it's your eye, which you will see what did you prepare. It's your eye, because it's like that. If my naked eyes is looking to this guy, and I see he has glasses, he has nice shirts, he has nice eyes, he has nice hair, he has. I'm not flirting with you. Don't worry. Okay, I can see him clearly. This is first. In electron microscope, of course, if you want to see very small insect or very small organisms or very small thing, you can go. I can't see it with my naked eye. I have to use microscope, optical microscope. Optical microscope. Uh, this is optical microscope. Okay, you can use optical microscope. It shows you some micrometers. Okay, and if you want to go deeper to like DNA, to check DNA or to check something in atomic scale or nanometer, you can't use this. Or this one is SIM. It can't go to nanometer scale, but it will go to micrometer scale, and you can see it. And this is TIM. Of course, it's huge because it has many sophisticated equipments and parts. But let's go to previous slide. Uh, of course, electron microscope. It's like electron microscope is like optical microscope, but it uses electrons instead of light. It may be transmission electron microscope or scanning electron microscope. And I just showed you the picture of these three devices. And let's compare between optical microscope and electron microscope. The optical microscope uses visible light, but electron microscope uses electron beam. With resolution, electron microscope light lambda is used around maybe the wavelength is 200 nanometer. Where in electron microscope it goes to 0.1 nanometer. The magnification in optical microscope it may be 1,000 or 2,000 times, whereas in electron microscope it may go to 1 billion times or more. Sample preparation in optical microscope is very easy and very simple, but in electron microscope it's little bit sophisticated, and I'll show you how. For cost, optical microscope anybody can use it. Like anyone can buy it. You can find it here in this university. I'm sure you will find many in this university. Okay, but in electron microscope, if you find one or two, it will be very enough because it's costly. Okay. For accessibility, anyone, as I mentioned, anyone can use it. In electron microscope, technicians, professional technicians, who will use it? Nobody else can use it. I can't use it by myself. I have to ask a technician, who is well trained to use it and make some samples for me in my presence. And this is another advice I want to tell you. Sometimes some people like me may give samples to somebody. Please make this as for Tim or for Sim, especially for Tim or for Sim. Okay, and you just take it. After some time, he will send me data through email. That's all. This is not good at all because you prepared these samples. You are the manufacturer of these samples. You know what you are looking for in these samples. So please, what will you do is you go to the instrument by yourself, sit with the technician just beside him, and look at your sample. Oh, I need this picture. I need this picture. No, neglect this one. This is not good one. No, resolution is not good. Oh, please focus on this. It's astonishing or it's surprised to have this particle here. Please have it. You understand what you prepared and you know what did you prepare. So please do it by yourself, in your presence, not by yourself, because he will use his machine, but you will use your eyes to check what you want. Okay. Another, this is the types. Of course, there is sometimes like compound stereo fluorescence. It's not our topic, but in here in electron microscope, it is TEM or SEM. Let's go to how it works. For SEM, for example, I will not go in deep in these techniques because even I can't, I don't understand all about it. Just I know what I need about it. Okay. In these techniques, in SEM, electron goes from the source to lenses which are just make it narrow and condense these electrons and accelerate these electrons through these lenses and the detector to know what the exact beam has, and then the sample, which is the pink one. Reflection of some electrons will occur, and then detector will detect these samples and show me the picture on the screen. This is it, okay? In case of scanning electron microscope, some of the beams electrons strict. Okay, it just says what I have just said. In TEM transmission electron microscope, the story is different, little bit different. How? Because this, of course, they have the same electron source and the lenses to filter and condense these electron beams and goes to the sample. After that, some electrons will pass the sample and lenses, and I'll try to see what the sample left or what are the beams transmitted from the sample, like this. An electron beam hits the sample and the transmitted electrons are magnified again because I can't see in this stage. It will be magnified again and again and again until I can detect it and see it. Okay, like this. Of course, this is. Of course, I want to say that we just mentioned that in SIM or TIM may go to more than million times. TIM and SIM may go to more for magnification more than million times. And for TIM, it has two types. The first one is older one, which is only TIM, TEM, and the newer one or the highest resolution one, which is HR TIM, which high resolution TIM. Okay, a high resolution TIM magnify to the atomic scale. We will see. Oh, this what is this? What is this? This is the sample holder. This piece of copper. It is seen. It is only maybe half centimeter diameter. This one, half centimeter diameter. This piece of copper, it's called grid. This is the sample holder. You just prepare your sample. I'll tell you how to prepare your sample. just take a piece of sample, a piece of this sample, and to put it in a solvent. This solvent will not solve this sample, of course. It will it will be a kind of suspension, even if in water or in alcohol or in other solvent, but it will be suspension. Okay. After that, you add this grit by this uh, 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 clips or something, and it will carry your sample on this grid. Okay. After that, you add it in the pink space. Of course, it is other. It is not simple like this. It's going inside the inside the instrument, and around it there are many lenses and many sophisticated parts. I'll show you what are the common microscope have. What are the common parts in microscope? The first one is electron source. This is the first. Second one is condenser of lenses. Both are condensed. Objective lenses. This is at object, which is the sample. And sample chamber. Of course, it has sample which you have holder. And detectors. These are common. But the difference is you will see the difference here. Only this is the difference between SIM and TIM. In SIM, the sample is by the end and it reflects the beams to show and you can detect the reflected beams. But in case of TIM, it transmitted the some of the beam, and then you magnify these transmitted beams and magnify again and again until you go to the scale you can see and receive these beams to a detector, and you can see it and study it. This is TIM and SIM images. I'm sure you can see clearly that SIM image, it detects the substance or the material you add, is a sample you add from the top like this. But in case of TIM, it sees in deep, it goes deep inside the sample, and you can detect. It's a very beautiful picture. That's why I present it here. It can detect the order and how are the atoms are arranged in on the surface. This is another example of SIM image, and this is other example of TIM image. Of course, you can see how the atoms are arranged and how much the picture is very beautiful. Now I think we go through TIM and SIM very quickly, and let's go to another technique if you don't mind. This is UV spectrophotometer. This is mostly common technique. In UV, it is before X-ray, as you can see. Its wavelength is longer than X-ray, but it is shorter than visible light. This is common one, as you can see. This is the sample holder, cuvette, which you put inside the instrument like this, but in the other part. This arrow should be on the left. This is spectrophotometer. I think most of you know it and used it. Okay, so in case of spectrophotometer, it measures the amount of ultraviolet and visible light that is absorbed, not adsorbed. There is a difference between absorption and adsorption. This is absorbed by the sample. Of course, the adsorbed light depends on the material you are using and how much functional groups it has which can absorb this light. Okay, identify the quantity compound in variety of samples. Yes, it identifies the quantity. Quantity means the concentration. Of course, you can do it. There is kind of it's very simple experiment and a very simple technique. UV visible UV spectrometer works by passing a beam of light through the sample and measuring the amount of light that's absorbed at each wavelength. Of course, the amount of light absorbed is proportional to the concentration of the absorbing compound in the sample. The more concentration means more absorption of the incidence light. Of course, it depends on a very old law, and it didn't change until now, which is Beer-Lambert law. A equals log I naught over I equals epsilon CL, where A, of course, is absorbance. Absorbance is dimensionless, and the I naught equals is the incident light, and the I is the transmitted light, whereas L is the path of the lens through the sample, which is almost 1 centimeter, and the C is the concentration. L, what is L? This is L. This is L, is the thickness of this sample. I think it is almost 1 centimeter or less. Epsilon is a constant known as the molar absorptivity or extinction coefficient. Let's go to this. How can we use this technique? It's very useful. I'll show you how much it's useful. UV spectroscopy is broadly classified into absorption, fluorescence, reflectance techniques, and something. Absorption, of course, it is fluorescence measures. It is absorption or reflectance spectroscopy. This is not our aim here. Instrumentation, it may be single beam or double beam. I want to go here. This is what will you use in UV spectrophotometer. What is it? You will go and make your experiment, take your sample, and add your the dyes. Of course, the dye will be colored like the left one. Okay, will be colored, and you check the light, and how much absorbance it will have. It will be very high. Okay, you go to your catalyst, add your catalyst, and make steering for some time, a time interval of 1 minute or 2 minutes or 3 minutes, whatever what you want. No, not what you want. I'm sorry. The controlling part is the reaction. If the reaction is very fast, you will have to take more samples at short interval times. But if the reaction is very slow, so you will have to take samples at much longer time. After starting the reaction, the concentration will be will decrease, as you can see in the right hand side. The concentration of green will decrease like this. This is concentration with time. And here on the left side, the concentration will decrease, means the intensity of absorbance A will decrease like this. And by time, it will decrease and decrease and decrease until it is very low like this. And this picture on the right side, it shows that the water is much clearer than the left side. Okay. If the concentration is high, then this absorption peak will be high. If the concentration is low, then the absorption peak will be low. And of course, whenever you add some, when you use some dyes, each dye will have its own lambda max, which you measure, and of course you trace the activity of the catalyst in this by this technique. This is, I will show you something else. This is one experiment which it's very famous, that for para-nitrophenol, it changes to converted to para-aminophenol. Of course, this is this one paper, one published article, mine. It is mine. at here you can see on the right side, it is no, it's on the left side, the difference between para-nitrophenol and para-aminophenol. This peak is maybe 300 something, and the para-nitrophenol, the peak is 300, maybe 390. And this is the decrease of concentration by time. It goes like this. And this is when we plotted the linear form of first order kinetics with time like this. And this experiment is very famous, which is the reduction of para-nitrophenol to para-aminophenol. And the left one is very harmful one, and the right one is very useful in pharmaceutical industry. By this way, we traced or we followed the reaction by measuring the absorption of para-aminophenol, para-nitrophenol, and para-aminophenol like this. One of the most important parts of using UV is the reflectance spectroscopy in reflectance, where you can determine the band gap of the material. Sometimes you need to determine the band gap when you use titania compound, titania composites, or titania added something. You need to use determine the band gap, and by this there is an equation you can use band gap, and new instruments also some softwares can determine it. I think one of the other most important techniques is the infrared spectroscopy. Infrared is very important. It's second one or same level of XRD. Even it is more famous or more common than XRD. And this is infrared just before visible, as you can see here. The wavelength is shorter or longer than visible light. In infrared, of course, it can determine the catalyst structure. And after you make absorption, after making absorption, you can detect what is the structure of the catalyst or what the surface of the catalyst has. Like if it has basic sites, acid sites, at this time you can detect or make absorption of pyridine. If you add pyridine to the surface after cleaning the surface by evacuation and heating, you add pyridine. Pyridine will be absorbed to basic sites and acid sites. It will give different peaks. Like if you add CO, for example, it will give it will give you an idea if the catalyst is distributed or there are some agglomeration which is centering of the catalyst on the surface, and NO and something. By infrared also you can trace, you can follow a reaction as well by in situ techniques. We will discuss it later on, inshallah. The most important, there is, it has different types like absorption, transmission, and reflection. Of course, this is IR. Of course, these are the advantages of using IR. It is non-destructive. It is non-invasive. It can be adapted in measuring in the reaction conditions like in situ. It can be used at high temperature or very low temperature, no problem. This IR studies done under real process conditions, yes. And the last is you can use reactive probe molecules to quantify and qualify and quantify the type of number of active sites. This is a chart of IR, and for this chart, I can tell you again, you will not invent the science. You will go to some tables like this. It has where is the functional groups can be detected in this scale. Okay. For IR, it can, if you make absorption for example, on CO, if you get a line or a peak from 2000 to this range, this means that you have linear CO on metal like platinum or copper or something. Of course, there is a difference, slight difference between each metal and the other one. And if you have bridged, bridged means CO is absorbed to two metal like this, triple bridged, three metal atoms like this. This means that you have condensed or not distributed. Your catalyst is not distributed well on the surface. And if you have geminal like this, geminal means two CO are connected to metal, or three CO are connected to metal, tricarbonyl. All of these, if you have special or detect peaks at specific places or specific wavelengths, this means that you have something on. You can see what exactly are there on the surface. And this is an example of using linear. It, this is real experiment on the left from this reference. And finally, thank you very much for your attention. Thank you. जैसे सर हम IR में फंक्शनल ग्रुप की स्ट्रेचिंग से पता लगा लेते हैं कि इसमें कौन सा स्ट्रक्चर फंक्शनल ग्रुप है। तो यूवी तो सिर्फ ट्रांजिशन बेस्ड होता है, यूवी स्पेक्ट्रोस्कोपी। क्या हम इसको किसी भी कंपाउंड की फंक्शनल ग्रुप या फिर उसके स्ट्रक्चर में जो फंक्शनल ग्रुप वो पता लगा सकते हैं बाय यूवी? So he is asking any for the characterization of any molecule, for UV can detect the functional group of the molecule. Yes. Like IR can analyze the molecule having the functional like carbon. UV detects the electron transition. Yes. Each technique has its space which works for, but it can detect transitions like carboxyl or something. It has some peaks detected, or if you have these peaks, this means you have this. If you know that you have, for example, if you have benzoic acid and you make UV, okay, and you detect a peak, this peak will be belongs to the effect of UV with functional group which is transition, which is carboxyl, okay. Of course, there is no table which shows that carboxyl will be detected at this functional group at this wave number, and some carbonyl will be detected here, and something like this. Of course, I think it's yes. Thank you. Sorry again.
Which technique is used most commonly nowadays, and what advantage does that method?
The most common is what you have.
Okay, in next lecture we will discuss, sir. Your problem will be solved by sir.
No. Do you allow me 10 seconds, okay? 10 seconds, I'll tell you. The problem is the most common, if I can arrange it, this is most common. For example, if you are working in organic chemistry, the most common will be just to check melting point, okay? Because each lab will have melting point. If each lab will have IR, so the most common will be IR. And the cheapest is the most common. The most available is the most common, okay? But you can arrange what you go to by expenses step by step about what I did already, okay? Okay. Any other question? Thank you very much. Thank you.
Okay. So thanks, Professor Zain Muhammad Ahmed Al Bahi, and he delivered a very informative and very learning purpose lecture. Okay, thank you, sir. Thank you very much. So now the time of tea break, and then after uh, tea, then we are again assemble at 11:30, most probably, or 11:15. So for the second lecture. Okay, thank you very much. Going for the second lecture, I would like to invite Professor Mannar sir to come on dais, and Professor Rajan Patel. please come and please come to our guest. Yes. जी, take a seat. Now I would like to invite Professor Rajan Patel to felicitate our guest, Professor Mannar sir, with a token of appreciation, respect. Yes. Thank you, sir. Thank you, sir. So now I would like to invite Professor Rajan Patel to introduce our guest. Please, sir.
Thank you, Professor Isaac. And it's me a great pleasure to be over here today. And first of all, I would like to congratulate Professor Raisuddin Sahab and whole Department of Chemistry to organize this fantastic GIAN program. I think this is the 37 GIAN program in Jamia Millia Islamia. So, and today with us, Professor Moria Sahab, my teachers in IIT Roorkee. I was did my MSc in 2002 from IIT Roorkee, and Moria Sahab taught us and in very well manner in organic chemistry. So, sir, thank you for your always blessed to me, actually, sir. So, currently, I am director of Center for Interdisciplinary Research in Jamia Islamia, and I'm in charge of CIF facility in Jamia Islamia. And as Raisa already maybe informed you that there is a visit of all of you there in RCF. So please welcome. I welcome you there. Please come on time. So Professor Moria, currently the professor and dean of faculty affairs in IIT Roorkee, and Moria published more than 170 research articles in peer-reviewed journals. He has been contributing higher education to the institutions in India as well as in abroad. He is also a editorial member of many peer-reviewed international journals like Inorganic Chemistry, Journal Journal of Inorganic Chemistry, NJC, and other reputed journals. He has completed many number of research projects from various funding agencies like CSIR, DST, SERB, and ETC. Sir also awarded many awards like Best Teacher Awards by IIT Roorkee, Best Paper Awards, and Good Researcher Awards from IIT Roorkee. He is a life member of many scientific societies. He supervised more than 30 PhD students, and he has delivered many national and international talks. So, and also, sir is uh, we are thankful to Amara sir. He always come when we required him, and he is very kind and helpful for all of us of you. So, sir, thank you so much for your presence over here today. And so now I invite you, sir. Please deliver your talk to this program. Thank you so much, sir.
Yeah, thank you, Rajan. Because it's my student, so at least I can call him Rajan. Thank you so much for introducing me here, and it's nice to be here actually. And I'm thankful to the organizing committee and particularly Professor Raisuddin sahab, who called me here to give this lecture. Possibly, I'm giving the first lecture in courses like GIAN, and I'm a little bit afraid of that. If I don't know if I can be for your parameters up to the mark or not. I'm not very sure. I'll try my best. Uh, see, basically, I'm a coordination chemist. In organic chemistry and coordination chemistry, that is my favorite. And within metal complexes, I'm known for vanadium chemistry. Vanadium chemistry, which is the most difficult one in India, 2-3 people are doing, not more than that, because the characterization, the one student asked for characterization is very, very difficult for such complexes unless you have most of the good techniques available. So, with the coordination chemistry, while I was in National Chemical Laboratory Pune, tried to learn some catalytic chemistry and then diverted partly myself to some other fields like one of them uh, I'm going to talk today, and well, is still continuing the vanadium chemistry for last 25 years almost, and I was surviving very well. So I feel that yes, I'm doing something at least. So okay, let's start with. So today I am going to talk about in this lecture that polymer supported heterogeneous metal complexes, how to characterize them, and their catalytic applications in various organic transformations. Okay, very first thing when we talk about the catalysis, I'll take back to like more than 200 years almost, when in 1835 Virgilius introduced the definition of the catalysis. You all know that this is based on the activation energy, right? But at the end, the catalyst becomes free from all and remains almost in the same condition. So with this, if you talk about the catalysis and catalytic products and their utilization, we look at the chart here, catalyst based technology. More than 90% of the products are processes in any field you talk about, whether it's pharmaceutical, industrial, petrochemicals, fertilizers, biochemicals, every field you find application of catalyst. Okay, so all fields is very useful. Me then when you talk about catalysis, then definitely two things you all know, that basic fundamentals, that what are the catalysts, maybe one homogeneous in nature, one is heterogeneous in nature. When you talk about homogeneous in nature, you all know that Wilkinson catalyst is a very popular one. We all know that Jesus salt having plenty applications. Other similar compounds, rhodium compound, lithium compound, when we talk about, they have a lot of plenty applications, and those are homogeneous in nature. And also you know that many of the heterogeneous now catalysts are known. So which of them is really good? That question comes. No doubt homogeneous is having tremendous applications. You all know that Ziegler-Natta catalyst, simple reaction polymerization. Wilkinson's catalyst for homogeneous, for what is called that hydrogenation and that hydroformylation reactions, etc. Okay, but whether the heterogeneous catalysts are good when we compare between homogeneous and heterogeneous, definitely there are some benefits with the heterogeneous catalysts. What are those? They can be recycled, they can be used time to time or several times without going to like diminishing their properties. While homogeneous catalysts, well, they are good, but at the same time they have a problem in separating them from the reaction mixture, because at the end we have to quench the reaction by decomposing the catalyst, because separation becomes very difficult. And then if separation becomes difficult, then either you continue, or when you need to stop it, then you have to break down the catalyst so that you can recover your catalytic products. So what is the solution for that? Solution is that make the homogeneous compound heterogeneous in nature, then it becomes really useful. So you can have a, you can enjoy the property of homogeneous as well as heterogeneous both together. Then recyclability becomes no issue at all. So then it becomes easy separation from the reaction mixture. You can just simply filter it. Okay, and they do not produce normally the waste. That is the beauty of the heterogeneous catalyst. And also when you talk about the last, meet the industrial demand of recyclability, because this is one of the major issue these days, whether catalysts are recyclable and reusable. Stability, recyclability and reusability, that is the major issue every time we talk about. Okay, so let's see that I have tried. In fact, in India, I was the first one when I was a PhD student about to leave. My supervisor said that why don't you start this field? Well, after PhD, getting PhD degree, you don't take interest what supervisor says by that time. That is the fact. Today that fact is fact. All right. But he said, will you start it? Well, I was forced to start because I had to get recommendations, right? to get somewhere postdoc or something. I started it. I learned some chemistry there. That was in my mind. And then next student we joined the group. He did the all other chemistry. I just handed over everything, gave all know how the this way to proceed it. So we started it. But when I started my journey for postdoc to the lecturer or assistant professor and the faculty position, I forgot that because I had to learn some more things. When we came back, then I thought of why not, after having some experience in a catalysis from the catalysis division of National Chemical Laboratory, I thought let's start it. So we found this is one of the simple material. It was gifted from the Thermax company from the Pune. They gave me like 500 gram this materials with this kind of a structure with chloromethyl polystyrene cross linked with divinyl benzene. So then I started thinking how to use that. So we started with this is a very simple reaction I would like to show you. You has this is CH2Cl group and the NH group there is available. They can condense very easily to form a covalent bond. And that was the beginning of this very simple ligand, very simple chemistry we started with. And since vanadium was the favorite one, let's start with the vanadium because I know something. So that was the output of that, and we could prepare assembly compound by this way. Prepare first the attach your polymeric materials with the ligand and then do the metal chemistry, what is usual chemistry. So this way it worked out. Other way that when you look at here, you have a COH group, OH group and carbonyl group. COH group is more reactive because you need CO minus that forms very easily. So the formation of the covalent bond between polystyrene and the COH group was very easy. So we started with this one stepwise formation. First you have to react with the say formyl salicylic acid. Then the next step like say base chemistry you react with the amino alcohol or amino acid compounds and then do the reaction with metal salts. As usual chemistry we do that and it worked out and we could prepare that compound. Okay, I'll show you some other way also. The same way when we extend it, then the question comes how to characterize. Very first question, characterization not an easy job because we don't know how to characterize polymer. Polymer IR will not give you much information, but since metal ion is attached there, nitrogen also is present there. First thing we can do that elemental analysis. If that gives you metal content, if it gives the nitrogen, then according to the formula of the metal complex, simple coordination chemistry fundamentals, we can calculate the metal to nitrogen ratio. Based on that, we can fix at least this is the compound, possible compound. Okay, so based on that, this has been fixed that, and you will see that there some nitrogen percentage, vanadium percentage. So when you convert into millimole, then you see the 1.3 to 1.06, almost like 1:1. So this is possibly the 1:1 complex formed in the reaction mixture. Okay, then the other characterization can be done. Other way there, you have a ligand here already available, react with the CH group, and look at there. Then you form the all the way, and then do the reaction with the starting precursor, and then finally see this is one of the way you can isolate right there as a methoxy derivative, or when you pass excessive oxygen, then methoxy group is lost and another oxygen group comes the diaxo. Why diaxo? We are more interested because their characterization becomes very easy. Why characterization becomes very easy? Because in the IR spectroscopy you are familiar with, and you also had some exposure of the IR in the previous lecture, where here we have a C vanadium double bond and the both oxygens are in a cis position. So cis position means if you have a V double bond O, they around 900 centimeter inverse one peak can be seen there. Maybe because it's poly material that may be weak, but when you have the two double bonds and the cis position, there two signals can be seen very easily. Cis and trans, you know that the fundamental principle. Okay, so then characterization becomes very easy, and you will see that after all this good thing came out, and we are able to publish it. Okay, another way that we have a NH group in the very first slide where I showed you that then now we have experience and we can go all the way around and prepare these metal complexes, different kinds of all sorts of compounds we can prepare very easily with that. Okay, see the another one. See, we have a SH group and COH group. SH group is weaker in finding S minus bond, but CO minus is very easy. So this we worked out, and we could prepare the another ONS type of ligand connected with the vanadium, and finally attach with the polymer to make it homogeneous in nature. Now, see the characterization a little bit given more detail. Ligand to metal ratio, you can find out. This is the two formula given where you can calculate the metal loading and you can calculate the ligand loading. Based on that, then the stoichiometry can be fixed of these compounds. See, this is another way. What I showed you that everywhere either CH group or NH group or OH group were present to coordinate to form a covalent bond with the polystyrene. Here, this is another way around. First, functionalize the chloromethylated polystyrene with, like, see, you have a their imidazole type of molecule in the NH. You know that it can coordinate, it can react to form a covalent bond. So convert the polystyrene into the that benzene hooked polymer, and then now there is one nitrogen which having lone pair of electron and which can donate the lone pair of electron to metal center and form a metal nitrogen bond. So that is strategy worked out very good, and we can also prepare this way the another molecule heterogeneous in nature. And the, since covalent bonding is with the vanadium is there or the nitrogen is very stable, doesn't lose very easily unless having very drastic condition. Okay, then characterization comes in the picture. How to characterize it is a difficult job. When we started this chemistry in 2002-3, we were lost how to characterize it. We were hopeless how to characterize it. But slowly the techniques came during that period when IIT Roorkee had only FE, not ACM. It was not available, but we could see at least there. The later the ACM also FE with ACM came, and there the beginning you could see the image of that, and that image gave some information. One is very light and one is a little bit dark in color. That gave some indication that yes, the heterogenization has been occurred, and the metal complex has been attached to the polymer with the covalent bonding, and then later through the SEM energy dispersive X-ray analysis we could see whether if ligand is there by looking at the nitrogen percentage, and then vanadium is there by looking at the vanadium percentage, that we were sure now that well this is the metal complex is anchored or covalently bonded to the polystyrene, or in other words that heterogeneous metal or catalyst has been prepared successfully. Okay, also we can record where this is a solid material insoluble in polymer is insoluble in any solvent. However, we can compare the UV visual spectra with the regular homogeneous compound, but since the material is insoluble, how to record the UV visible, that is a challenge. So we found one techniques where the metal complex, heterogeneous metal complex, is grinded very, make it a powder, and then add some nodule, make it like a paste, semi-solid, and you just simply stick on the cubit, whether you have a quartz cubit, you paste it. So you have a one simple nodule pasted and other one having your metal complex pasted, and do like a regular UV visual spectroscopy, and you can get some feeling or some observations through that one, and that worked very well. You have to adjust concentration several times, but you should be able to get the visual and UV visual spectra of these compounds very well, and can have some information after comparing with your homogeneous analogs. Then EPR state works very well. EPR in the solid state. EPR also can be recorded in the solution DMSO. Just I mentioned that by grinding your sample into first and then put it in the DMSO, the suspension, and freeze it -70 degree. That becomes almost like a solid, and you can record the EPR. EPR worked very well because EPR is very sensitive to the metal ion. Okay, so see 8 lines EPR spectrum, and you will also do that in the two different way. One is solid, one is dissolved in DMSO. At -70 with the homogeneous and the heterogeneous, both are compared here. You see that all signals whatever available in the homogeneous system is available also in the heterogeneous system. Means the compound, if this is vanadium 4 with only one unpaired electron in the d orbital, so easily can be seen through that, and that can be interpreted that we have a metal complex form into the heterogeneous system. Now, see, this is one of the technique that is called the 51 vanadium NMR. It's a very difficult challenge because it doesn't give really. We tried here at our place now. This was recorded from the Portugal, from University of Lisbon, that they could record it, but we tried here. We have to run several thousand scans to get 51 vanadium NMR. So that was the difficult challenge. We dropped that idea. But anyway, that give you the feeling that we can also record 51 vanadium NMR. Proton NMR is not possible. C30 NMR is not possible. The reason you know very well that because a lot of carbon and hydrogen in the polystyrene. Okay, that is not possible. But metal center that can be detected here, and based on the peaks observed at say minus 535 in this compound, and upper one there is 535 and also minus 504 signals, major signal that is for the diaxo, and then the other signal that came that we interpreted it based on the literature that this is the possible interpretation of this 51 NMR, but it worked, and that showed that we have a metal center or we have a metal complex anchored or immobilized on the polymer support. All right. Now, after doing that, now we tried different catalytic applications. Characterization now by doing all these different using different techniques, we are familiar with that the compound has found, and always compared with the homogeneous metal complex. So we give the idea how what is the structure possible in the immobilized materials. Then we started some catalytic activity. I'll show you some simple catalytic activity here. That is one of them very popular one is that oxidation of sulfide, organic sulfide, because this oxidation, if you look at that sulfoxide and others, they are sulfur drugs mostly having various double bond or two oxygen, okay, double bond, oxygen, sulfur, oxygen, diazo group. So we tried it, and see the conditions can be fixed, that is called the optimized condition to get the maximum conversion or maximum oxidation. So what we can do, we can optimize using different loaded of different loads of the catalyst. You can also change the what is called that oxidant. You can also change the temperature. So by doing all these things, once we get the highest conversion, then we can check all our catalysts under that particular condition. We will see that we have four different catalysts used here. Some of them are polymer supported and some of them are no polymer supported, but the activities can be seen here with time because this is recorded at every like half an hour using gas chromatograph, and conversion can be seen that, and the details can be seen here. See the polymer supported and comparison with the homogeneous catalyst. You see that polymer supported catalyst giving very good conversion along with good turnover frequency and sulfoxide and sulfone selectivity. You can also calculate through the gas chromatograph by using internal standard. We are not familiar those days how to use external or internal, you know, um, standard. So what we have done, we have used the uh, what is called that area under the peak. A vanadium 4 center is EPR active. When we had H2O2 is oxidant, it oxidizes vanadium 4 to vanadium 5, that goes from D1 to D0. D0 means there is no electrons, so you should not be able to see the EPR. So when we have done that, when you look at there, adding A, B, C, D, some small amount of hydrogen peroxide, some more peroxide, what happens here? The signal is going weaker and weaker and finally almost becomes like a flat. But when we add methyl phenyl sulfide into the mixture, again record the EPR, what will happen? The peroxide species formed during the reaction with the H2O2, the oxygen is transferred to the sulfide slowly, and sulfide is converted to sulfoxide and sulfone. So oxygen is, you know, you are taking out oxygen from the peroxide species and then converting back to oxyvanadium 4. So your then signals are again regenerated. That clearly shows that oxygen is transferring from the peroxide species to the substrate and is converting to sulfide and sulfone. So that gives very good idea about the possible mechanism, during the reaction, how is it going on. Similarly, 51 vanadium techniques, as I mentioned, that it is useful and gives some signals. So this is done by the homogeneous system only, not with the heterogeneous system, because heterogeneous system gets a trouble. But you can see that in the beginning there are two signals, one major signal that is for the uh, after addition of this is one of the diaxo compound. So when you have a diaxo compound, you will see one big signal, and some any other species, isomeric species, small signals can be seen right there. And then when you add S2O2, you should be able to see another peak generation of the peroxo species along with the diaxo. So look at there, the peak around that is 600 something, 579, another peak is generating. Okay, means diaxo is going to the peroxo, and when you add a substrate, then the peroxo species will break down as soon in the top of the compound. You will not see the peroxo species formation in the solution. So that clearly indicates that there is a transfer of oxygen from there. So peroxo signals is going back to the diaxo, giving only the major two signals what is expected. Okay, and the other signals, because in the solution that will not remain only the diaxo, maybe some other species forming, maybe some DMSO interacted species, maybe some other species. So more than one signals are always expected. But that gives idea that this is the way reaction mechanism going on during the reaction. Okay, so based on that, the reaction has been proposed that the where diaxo species is going to the oxo-hydroxo species, and then going to the peroxo and with H, and then oxygen is transferring, giving to sulfoxide and sulfone one by one oxygen transfer. So reaction mechanism can be proposed for that reaction. Okay, now after getting the idea of the oxidation of sulfide, this is one of the very, very important project where when we have a organic sulfides, those organic sulfides found in gasoline, petroleum products like our diesel and petrol. These are the challenges for the industrial people like IIP, Dehradun, Indian Institute of Petroleum. They are doing a lot of research for desulfurization. That is called desulfurization. What they are doing is basically oxidizing organic sulfides to the sulfoxide or sulfone. Okay, so they are making it soft because these are the materials which are actually creating problem. These are the mixture present into their mixture. So what we have tried here, we have tried to oxidize different organic sulfides. Different types of sulfides you will find there, and of course we have used this catalyst. Okay, how have you done that? We have prepared a solution of like a 500 ppm in a simple N-heptane. So you are making like gasoline, you are making like petroleum products. Okay, and then we try to catalyze the reaction and looking at how much ppm sulfide is remaining the other way around through the gas chromatograph, and that gives wonderful idea that how much conversion had done or does desulfurization has been done. So when you look at that 500 ppm initially concentration was taken, and after desulfurization, this is the ppm we obtained it. So that shows that the sulfur removal or oxidation of the sulfur has gone like this way, like almost like 87, 88, and 89%. We are able to demonstrate it, and that actually give you a very good boost up in this chemistry, and we were able to publish this paper in organic chemistry very simply. Simple chemistry, but it worked very well. Okay, so you will see that also with the regular homogeneous catalyst, the conversion is very much less than their heterogeneous system, and the beauty of that was that is recyclable. We could filter it simply, wash with the acetonitrile, dry it 120 degrees say, in like a regular air oven, and then reuse that. It was very good, reusable. So that worked out very well. Now, see, this is another reaction we have tried with the benzoin. Benzoin gives you 4 different products. Those products can be analyzed by gas chromatography, different products, and based on their GC mass analysis, mass spectral analysis, we could assign all these products like going major into the benzyl, then we have methyl benzoate, benzoic acid, and we have a benzaldehyde dimethyl acetal using this catalyst. Okay, and details are given here. Again, we can optimize the reaction conditions by varying say the amount of oxidant, amount of catalyst, and then we can analyze it. The analysis is a very, I mean, it's not easy, it's time taking, because every product at every half an hour interval you have to use it and characterize using just gas chromatograph. So for 400 minutes continuous analysis for every half an hour and analyze those, and then it can be seen that benzoin is going from almost like 90+% is conversion, and then the different products are forming, and you will see that benzyl initially forms in a good amount but slowly converts into other different products, which is expected, because then the changes in the that one from the benzyl to the other products are expected, because for the decomposition of that, for the oxidation of that, so the all four products have been analyzed that, and see the conversion here, and then the product selectivity, that benzyl is still the higher side, is not that bad, but along with that your D product, that is benzoic acid, it forms a much, that is expected, that because it's further breaking and oxidation of that one. This is parachlorotoluene. This reaction gave us very hard time because this parachlorotoluene oxidation is very difficult. But we could oxidize, though yield is percent conversion is very, very poor, but we observed that there are at least 5 different products. Characterization of products itself is a challenge, but we are able to identify with the help of gas chromatograph, and these are the catalysts used for that. And when you look at the data here, the conversion is, when look at the how much? Maximum 12%, no, not much conversion, but whatever conversion based on that, at least the different products can be analyzed, because gas chromatography require only the ppm level concentration. There we can go for that and we can characterize that. Okay. Now, as I mentioned there, this is stable catalyst. EPR can be very helpful, so I will not go for that. Then this is a regular, like a substrate across the world. People first start with whether cyclooctane or cyclohexene can be oxidized using catalyst. It's standard. We have also done that. And these are the catalysts used here is shown. It is some copper catalyst and vanadium catalyst, and this gives at least 4 products. Okay. Those days we were not much familiar with the catalytic system, but still. Then later we have improved that, how to improve the conversion of the cyclohexene, to epoxide, because epoxide is a useful product. So we have later found out how the yield of the epoxide can be improved, but whatever data we had during those period, and you will see that at least 4 products are there where we have a cyclohexene oxide, cyclohexanol, hexanone, and cyclohexene 1,2-diol. Okay, and product analysis may be given in the next one. And then this reaction we have done, this is one of the very important reaction. Why? See, it's so simple reaction. I had given this project to MSc student in the 4th semester for the simple project. Just see that if the reaction works or not. See, this is bromination using potassium bromide. One of the very important reaction shown by the that is called enzyme haloperoxidase, vanadium haloperoxidase enzyme. So vanadium can be used as a model system for haloperoxidase activity, where KBr in the presence of H2O2 and acid can be converted, can do the bromination. Okay, you remember the Br minus is going to Br plus and then attacking it and making the brominating the product. Okay, so reaction worked out very nice. Simply take a water, add a small amount of catalyst, as much small you want, just add 2 crystals of the homogeneous catalyst and add a sulcidated water. Sulciate is not soluble in water, that is like a suspension, and when the reaction starts, you will see the white solid coming out. This was wonderful to see, so excited to see this chemistry is working very well. So we try that with using this catalyst, and then I gave this real project to our one of the MTech student, and you will see that the paper in catalysis communication worked very nicely. A simplest reaction, I would say that, and still we are using that, what is called the basic principle of haloperoxidase activity for the good molecules as well. Okay, so what? So you can look at the conversion. Conversion is more than 80% in most cases. and we have a 5-bromo salsylate. That's a fundamental principle. Okay, that 5-bromo salsylate is giving, and some other products. Other products are, those days it was very difficult to characterize because that time we had no GC in our lab. Usually used to go to the chemical engineering, or I had sent particularly for this one sample to National Chemical Laboratory. So they gave, this is the major products, other products we are not bothered about that. Anyway, that we still worked it because that gave a very good yield. Okay, and then this is usual uh, alkene oxidation reactions. You will see that. Okay, terminal alkene that giving you 5 different products of all products. What we expect that styrene epoxide is the most possible product, but that is converting into, in fact, the ethylene oxide, sorry, styrene epoxide forms at the very beginning, but it goes to different products through further oxidation. Okay, and this is the catalyst used for that one. So those very traditional reactions, then we thought, okay, let's try some really organic transformation to do some organic chemistry here. So one of the reactions that is called the hydroamination, another one is oxidative amination. What we have here? We have a alkene, we have a primary or secondary amine. In presence of catalyst, you find 2 products. If you know that Markovnikov and anti-Markovnikov rule addition, you have a 2 products, Markovnikov and anti-Markovnikov. Which one should be higher in yield? Because anti-Markovnikov is more favorable because less steric hindrance presence in that, and that gives you 2 different products. Okay. Similarly, oxidative oxidative amination. Again, you have a primary or secondary amine. You have a then oxygen now. Other one is without oxygen. So there again you get 2 products, and what is called that anti-Markovnikov is always higher in yield. So one by one these reactions will show the product here, real products. We get the 2 products. The 4 reactions are shown here with the secondary amine. Okay, and one side is primary, and other side is secondary amine, and you will see the products. Okay, and we have LIG. This is the catalyst used for that purpose. Okay, and see the conversion very good, giving you almost like 65 to 80% conversion, and then Markovnikov or anti-Markovnikov. As I mentioned, the anti-Markovnikov always higher yield because of the uh, less steric hindrance available during the reaction. Okay, so all data are presented here, and this NMR 51 NMR spectroscopy, by using the homogeneous analog, we are able to predict the mechanism, because when we do that, see, in the beginning we have a pure catalyst, homogeneous, and then when you add diethylamine, you see the changes because diethylamine is interacting with the metal center, giving the change, and then you add also styrene, then again change you will find that, and when you add excess of styrene there, then the almost original position coming back, that shows that reaction, that amine in the beginning interacting with the metal center, and then in the presence of styrene, that product is forming, giving you the final products. So based on that, we have tried to propose this mechanism here through Markovnikov and anti-Markovnikov. Both products are shown here how it forms. The possible mechanism always. Now this is for the oxidative amination, where all products are shown here that forms catalyst. This catalyst has been used there, and see that conversion is approximately 70%. Markovnikov and anti-Markovnikov. The same way, the yield of anti-Markovnikov is better. Okay, so of course, based on again the 51 vanadium NMR spectroscopy, we were able to predict the mechanism for this compound, this reaction. So up to that period, we have tried to, summarize, review all these studies. One of our review here that is published in say 2011. Then we based on the students, of course, the chemistry proceeds. If you don't have a student, are not interested in polymer supported, doing the vanadium chemistry, taking the challenging job is better. This student, one of our Bengali student, he was running out from doing the all good vanadium chemistry. So I gave him, okay, let's do with the polymer chemistry. And you do this, you see that this is molybdenum. Okay, then another change. But the molybdenum means chemistry is not less important. Chemistry is again important. Chemistry, I will show you how. So the preparation, now you can feel that the preparation is not much difficult. This is just a generation gap to show the fancy way the polymer, that's all. Okay. And well, of course, the generation is more intelligent, giving more, because we have everything now on the laptop, everything available. The benzene ring. I hate that. Why are you coloring benzene ring? But a student do that. Okay. So that's the way. So the chemistry work out very well. But here we have used starting material MOO to ACSE2 to prepare first that particular compound, dinuclear compound, and then in the bottom and you the hanging is that ethyl benzimidazole group, methyl benzimidazole group where NH group is available. So from there, this covalent bonding can be done, that can be formed there, and so this is highly stable. Now we have more techniques available, right? Those days techniques were not available. So now FESM with EDS also you have a what is called that metal content, more better way you can determine it. Okay, so all colored pictures, and you have see these things are shown here, metals, and between these figures you will see that the uh, elemental mapping can be done very easily, because you can see the different dots, and then everything can be corrected. Okay, so elemental mapping gave a very good result, and it's with FE those things can be seen very clearly. Earlier it was only black and white system, now we have a colored one. So the better way is can be seen. Okay, because the changing world, better instruments, more sophistication, more precision. Okay, so and then UV visual, you will see that as I mentioned, the UV visual very easy to characterize, and also for IR, this system is very easy to characterize. Okay, we have a diaxo cis system. It's same way IR. I have not shown IR here because it's a simple technique, but UV visual can be seen. There is no electron in the d orbital, but still charge transfer transitions can be seen, and also the bands due to the ligand that is expected only the UV region, all can be seen very easily. So we have characterized it. Say the more detailed way, the simple way it is given here. Okay, and then for the other metal center. Oh, thank you. But it's too cold. I kept. Okay, so all elemental mapping can be done. Okay, after that, look at there. Best way. Okay, do the elemental mapping, go for that and characterize it. Now what we have further? XPS. XPS gives you perfect information about the metal ion present, because you will see that all peaks can be seen for the even carbon with the nitrogen. We have a carbon and double bond, everything, and also metal mapping. So it XPS gives all information whether the C-double ion group is present there, nitrogen present there, carbon attached to the nitrogen present there, also metal center present there. So all information can be gathered together for perfect characterization. Also the atomic force microscopy, AFM. When you do the reaction in the beginning, when you have AFM, their metal centers, everything are aligned well. Sharpness you will see that in the beginning, and then roughness, height you can see that here. Average surface roughness 16.21, and when you have a PS1, that is catalyst, okay, then 4.0 surface roughness has gone down because of the complex formation. All right, and then also you will see that the after recycling, surface roughness has slightly increased because part of the things has gone, possibly the leaching, but those were present on the surface, that is gone, but still metal is present, the metal content is very good in that one. So all PS1, PS2, 3 catalysts were prepared, and then by getting the surface roughness, we can get the idea how much it is, anchored there, and after catalytic cycle is going away or not. So that can have idea. Then this is one of the reaction we have tried it, because why we have tried this, you will see that all is biomolecules. Okay, chromine, cyanochromine molecules, these all are having different biological activities. Okay, so idea was here, can we do the similar chemistry we prepare through catalytic reactions, that is called multi-component, one part multi-component reactions. All organic chemistry student must be familiar with that, where three components can be mixed in the reaction mixer. And when you have a catalyst, do the catalytic activity and get the products. So look at here, we have taken three different molecule like coumarin, resocinal, and 1,3-cyhexanedione. you have a malonitrile, and you have aldehyde. Okay, and three different types of reaction we have carried out, and say yield is giving really good, more than 85% yield we are getting. And the beauty of this reaction is the selectivity. 100% selectivity pure products. You do not require chromatography, because organic chemistry means chromatography. That is sure. Any compound you make, heterocyclic compound, you have to, unless you characterize by purify by column chromatography, you are not good to pure products. But this is giving almost like 99 plus percent purity. Okay, so we have prepared this compound, and to prepare that compound we have just simply excuse me, optimize the solvent. Okay, so solvent, when you look at there, ethanol gives really good result. And ethanol is supposed to be very simple, what is called that a solvent, easily available, and it's a green solvent. Some reaction was what in water, and some even without solvent we can go for such kind of reactions. Okay, so we used it, and then using simple ethanol, then we have optimized all other reaction conditions like catalyst amount excuse me, catalyst amount, time, how much time it takes, whether it's use a reflux temperature, other temperature, and yield. You will see that it's going almost like भाई ये तो गला ही खराब कराएगा। हाँ, आप चाहते हैं कि हम यहाँ से जाए और गला खराब करें? हाँ, मुझे तो यही लग रहा है, साजिश। Okay, so you will see that the simple with how much catalyst you have, a 10 milligram polymer support. 10 milligram is a very small amount of catalyst there. Okay, so its reaction is going up to like 91% with 199 plus selectivity. Okay, and you see that all compounds we have done it with homogeneous, we have also compared, and also the last one are the recycled catalyst. So you got the conversion, it's going very well, and catalyst can be recycled at least 5 to 6 times. We have done that and working very well and getting the good result. How to recycle it? Simply we can filter it out, because its polymer beads are there. So using simple filter, because organic dissolved in certain solvent where your product is soluble, catalyst is insoluble in any way, that can be filtered and can be reused. Remember that when we say reuse, if you are filtering it, being a human, we are going to lose part of that catalyst. So in next cycle, what we have to do? You combine two such cycles, products separated, the catalyst of two such cycles together, and take the same amount what you require it, and then you can proceed with that very easily. Or you filter it out, add substrate and products right there, and we can do further reactions continuously up to 3 to 4 times very easily. It works very well. That case reaction will perform little bit poor and poor after 3-4 cycles without separating from the reaction mixture. Only what you are doing there, adding the solvent, removing the products, and then again adding the all substrate, catalyst, oxidant, etc., going for that reaction. It works, but so that reaction yield performs poor. But you see that all products we have different products, we have prepared with different derivatives, where we have electron withdrawing group, electron donating, all are there. Electron withdrawing group was a little better, getting a better yield of that, but giving you good things with recyclability. This is one of the good part. Now, so different, what is called that study, we were able to propose this mechanism, because this way we have also tried to isolate intermediates to propose this catalytic cycle. Okay. Now look at this 91 to 85, where we are using continuously without removing catalyst from the reaction mixture. Only this filtering out the catalyst, filtering out the products from there and reusing right there. Okay. Now, after catalytic runs, we have tried to characterize again all materials by all spectroscopy IR. When you look at the 911 and 943, that is for this cis diaxo compound. We have done UV visual, we have done FESCM, elemental mapping, everything, and also we have done XPS, getting all peaks, whatever possible peaks were there. Okay, so we have a more what is called the characterization techniques available. So definitely quality of the materials your study has gone up, and when you see that published in chemistry European journal, a very high impact factor. Okay. Oops. Saved. All right. So now this is the another simple molecule, and then immobilized on the polymer support. Now the advanced technique and student third generation, right? All right. So this is the molecule, and then see TJ characterization. You will see that very stable. That means metal oxide has formed, because polymer means 100% has to go out. So whatever metal oxide, from there you can have estimation of metal content, as well as through ICP-MS you can have a metal content. Through FESEM elemental mapping you can have a metal content estimation, and you can compare all three and should get all three almost same. All right. In IR, two bands, that is for the vanadium diaxo group. It can be seen. UV visible. Now I vote for that. And now this is another reaction that is called hydropyrimidine. Hydropyrimidine owns. Okay, hydropyrinones. This is another biomolecule, and we have tried this reaction with three components: aldehyde. Now we have a urea, and we have a ethyl acetate, or you can say the beta ketoester, and the product formation. The reaction works very well. See, the conversion is going almost like 85% yield, and the beauty of this here is that you can separate the product by dissolving it, and then just evaporate it, you get the compound, and you can crystallize it. You don't need to go for column chromatography. That is the beauty here. Okay, so the isolated yield in optimization condition is going almost like 95%, and all products, and this is both way. We have isolated yield, and then we have a almost crystallize that, or recrystallize, you can say that simply. Both yields are given here, working very well, working very well, and it's pure. That is the beauty, it's pure. Thank you. You thought of me. Yeah, thank you. रईसुद्दीन साहब को तो अप्रिशिएट नहीं करेंगे, उन्होंने ठंडा पानी पिलाया. Yeah, we have all compounds prepared. Not only plenty of derivatives, we have prepared it. Okay, and then we have also tried to check the recyclability. It's going keeping very well, keeping very well. If you want to have a 95% conversion, then what we need to do? Two cycles, as I mentioned that, isolate, separate the catalyst, combine together, and take the exact amount what we had taken in the beginning, first time. You will get almost same amount of conversion there. This is just by separating it and doing catalytic reaction within the reaction flask. Okay, so that can be done, and based on the different study, we have tried to give the, through DFT. Actually, we have taken help from one theoretical chemist. Through DFT, we have tried to give the catalytic reaction mechanism for that. Okay, now I'll move to the other products. See, look at here. Plenty of compounds are shown here. This is related to 13254 trisubstituted imidazole. Imidazole containing molecules, when you look at their biological activity in all, whatever you think, even in all directions, these are very well known. So biomolecules, the key imidazole are there, are in all compounds. So how to prepare such compounds using our catalyst? See, this is another catalyst. We have designed it. Okay, and this is for the homogeneous compounds. First characterize it, and then compare all activities. Now you know that how to prepare this compound by covalent bonding with that NH of the benzimidazole. Okay, and this is the one where the simple reaction is shown, is simple representation of the reaction, where you have aldehyde, you have a diketone, different one, and you have a ammonium acetate. When you use urea, that will give a different product. When you use the some other ammonium compound, that gives different. Here we are using ammonium acetate. Ammonium acetate giving you the ring like imidazole type of compound. Okay, and then all sorts of product with the different derivatives. See, electron withdrawing on the benzaldehyde, electron donating on the benzaldehyde, all can be used and the different products can be prepared. Beauty of this one is the last component, look at there. We have a bisaldehyde, terephthalaldehyde, that works very well also. There are two different aldehydes on the both sides, and both aldehyde groups are giving two different benzymetal group joined through the in a para position, and thus giving you, and also in the good yield. It's not bad yield, 83%. And beauty is that it's pure compound. You don't need to even crystallize at this point. You can get the NMR. Well, if 500 NMR is giving no impurities, I believe that this is the best. 99+ % purity of that. Okay, and they say that complex 1, 2, 3, 4, and then recycle 1, 2, 3, 4, 5 cycles. Working very well. 93 going to 84, but it means 84% is still after fifth cycle means a good one, and can be used as an industrial catalyst. I believe that if very well done under those conditions. Okay, so they based on different studies, catalytic reaction mechanism, that is important to give that. The reaction mechanism has been performed, where if you are a organic chemist, some of you will know that Nonangel reaction, Michael addition, other things, all basically based on those what is called the reactions known already. This kind of reaction mechanism has been given. Okay. Now this is another molecule. Okay. Now here what we have, benzyl parazolyl barbiturates, and other one is okay, this is one of them actually, and benzyl parazolyl barbiturates, and you have bioactive pyrazoles. Both are actually very similar molecules with a small difference only, you will see that. And again, when you look at their properties, with the having that key group of that barbiturate or that pyrazole, and their applications, we thought that can we do the reaction, catalytic reaction, and prepare those compounds. So now here is another vanadium compound immobilized on the polymer surface, so heterogeneous compound. And this is one of the reactions shown here. We have a beta diketone, we have ketoester, and we have a hydrogen hydrate. Oops, NH2 1, that 2 has gone, right? Do you see there? NH2, it should be NH2, NH2, hydrogen, NH is on there. Okay, so it should be NH2, and then you have a this another molecule there, benzene hydroxyl group, and then this goes the reaction like this way. There is a controversy in the literature where people say that this actually they what is called the cyclize and give you the cyclic products, but we observed that this does not form cyclic products at all. It gives the this ionic compound, and that is stable even at any condition, doesn't go under cyclization. Okay, so the scanning of the solvent, and then the catalytic reactions and reaction products. All reaction products, you'll see that yield is very good. And again, the beauty is that yes, we can prepare it with a good purity. We have recorded only just by simpling it, what is called that filtering it, and we have also recorded after simple crystallization. And after crystallization, these yields are reported and giving you very good yield. Lot of products, all with different electron withdrawing and electron donating group. Okay. Then only one case, that is exception. Why in this case? Because here we had hydroxyl group that is related to salicylaldehyde. In case of salicylaldehyde, only we observed the cyclase. It was very unique one. In all other cases, we did not find cyclization. The only one. Okay. Why it happened? And also, since it was different, so we thought about, okay, let's try that, have a crystal structure of that, because it's crystallized out very well. And so you see that only cyclization. This was exception to all other products where you have only benzaldehyde with different derivatives. Okay. So, and then you have the other one that is now paranoparazole. Again, this is called uh, four component reaction, but in this case, since see the same reaction is carried forward, NH2 NH2 should, where is NH happened? Okay, and then these two reacts with and form this one like in the previous case, and then when you have malonitrile and aldehyde, that gives you this product. Very similar product like earlier, only we have changed the what we have changed here. In that case, I will show you where it's gone. We have a triketone, and there we have changed it to the other one, simple aldehyde. So that becomes paranoparazole. And we can prepare all sorts of compound, and at least almost like 15 compounds we have prepared it. Okay, part of that are shown here. Beauty here is that to propose the reaction mechanism for such compounds, if one can isolate intermediates, at least few intermediates of the catalytic cycle are characterized by any maybe GC-mass, maybe HRMS, and then it becomes better. So what we have found out that in the beginning, like a beginning, when you combine these two, this give you the intermediate which can be isolated, and these two reactions, NH2 NH2 is known, and this forms the intermediate can also be isolated, and these two compounds intermediate can be reacted again in the presence of catalyst and give you the product. So you have we have isolated one intermediate and second intermediate, right, two intermediates in between, so that gives you the perfect reaction mechanism, that how the reaction is moving during the catalytic cycle. Similarly, for the other paranoparazole, see we have the reaction of this aldehyde and malonitrile give you the intermediate which can be isolated very easily and characterized. And see in these cases at least four compounds we have isolated and characterized it. And the other one which is well known in the previous section I showed you. And these two reactions can be combined together in the presence of catalyst and give you the product. All right. So based on that, this is the reaction mechanism. It looks very complicated. Okay. And believe me, drawing this simple mechanism took me a lot of time. Any student, we spent days and days how to give this mechanism, because characterization of intermediate, isolation there, characterization, and then finally putting in the form of a mechanism as a difficult job. Okay, this is under investigation still further. We have just submitted it. I don't know the future of this. We have submitted for publication. Okay, so I think almost 1 hour over. Huh? So finally, I'm coming to an end. Definitely, uh, this whole works started. I think we started in around 2002, and journey of the 23-24 years with the help of only the Thermax. Thermax, they are preparing resins based on the polymer in the Pune, and two times we got 500 gram gift of polystyrene from there with almost chloromethylated. We requested that we need it. They prepared it, and then after all and also they give it. So we're really thankful to those, because of this polymer, we're able to publish I think more than 50 papers in that area, and all good quality journals we are able to publish it, because chemistry we learn it, and we are the only one major in chloromethyl polystyrene across the world. We are doing it well recognized. Of course, the DST, Science and Engineering Research Board, now it has changed to NRF, and Council of Scientific Industrial Research. DST was so generous in 2010, because after doing a lot of catalytic chemistry, we requested for gas chromatograph. So exclusively for our lab, we got a gas chromatograph devoted for my research group, and it's still working very well. So 2010 we got it, almost 15 years over. Normally, instrument doesn't survive, but it is surviving. It's still, and whole department is using. I allow to whoever wants to use it, and it's working. If anyone interested here can come and use it. Most welcome to all. And thank you so much for your attention. Yes, any question, please. Yes, you got all answer your questions in your mind. But yes, sure, please. Uh, Polymeric metal complex in polymer. Okay. I didn't say not possible. You cannot get any information out of. You can do. You can record solid state NMR of that. Okay. Immediately you can do that. Liquid is not possible because that is not soluble at all in any solvent. Solid state NMR record it. What you will get it? CH, a lot of CH band that will cluster at one place, giving you a huge peak. If there is no functional group available, and if any functional group there, that will like 100% to 1%. You won't be able to even see that or characterize that. That will be a major challenge. Uh-huh. Ah, you know the fundamentals. I don't have to tell you that. When you have a paramagnetic compound, well, of course, NMR can be recorded. Nowadays, facilities are available. 600, 700 megahertz, you use it. But
Yes.
what you will get? You will get only broad peak because you have a paramagnetic center that will interrupt your or make your things almost like a corrupt. You will get only broad peak. What you will get? Only partly information you will get it, no other information. Okay. Yes, if you have a metal center and if you can record like EPR due to unpaired electron, and if you have a some diamantic metal center like vanadium, I told you that. Okay. Purposely, when I'm talking about vanadium, we are struggling with the 51 vanadium NMR. We had 400 megahertz facility, but we are not getting 51 vanadium NMR. वो क्या बोलते हैं, एनालिस्ट ने हाथ खड़ा कर दिया, बोले नहीं हो सकता साहब, मुझे आता ही नहीं है, ना हम कर सकते, ना स्टूडेंट पॉसिबल है. ओके. Then in 2017 we went to DST Fest. I was head of the department and tried to get 500 megahertz NMR purposely. And then before placing the order, I discussed with the person whether 50 NMR is possible or not. He said it will be possible. So we are getting all now 51 NMR, in our department, and I'm very happy. So because of that, I used to give at least 2 authorship in my paper, because simple as to go to different country, they are recording, giving the data. So now we are in our hand, we have that facilities we have. We are no less talented than the other any country people. I'm very sure in India we have plenty of talents. Students very talented they are, because the all facilities are available. Then go there, the outside see they do wonder. So now things are available, you can do that. So when you have a metal center and if you can record NMR, oh yes, you can do that. Yeah. Any other question, please? Sure, please. You are the boss of the today. Yeah, you
Thank
can
you,
do
sir.
that, please.
Sorry, you have done a lot of work, and I have seen a very nice, means best molecule you have synthesized in your laboratory. And I need to ask, you have characterized the molecules by using the various techniques, and some of the molecules they are in crystal form. So I have seen all the slides and seen all the molecules. They are more efficient, I think so, because you have synthesized and characterized. And I need to ask, these molecules can further applicable for biology purpose and other purpose. So I need to ask.
Yeah, definitely, it's a very valid question. When I gave you background, these are biomolecules. Okay, definitely. If I get one biolab which can collaborate, we can do that. We can prepare more complicated molecules. See, what I told you in the beginning, I'm a coordination chemist. I learned catalytic chemistry in between and doing chemistry. I'm a chemist, an organic chemist, converted to partly catalytic chemistry. Still doing a lot of vanadium chemistry than this chemistry. This is the side business. More the real business is something different. Definitely vanadium chemistry. Okay. So our aim was or is to do the chemistry. Okay, I leave the resting to biochemist, biological chemist, or other person who are doing such kind of activities. We can prepare even typical molecules, no doubt, because since we are having limited facilities within the department, within what institute we have, what are you saying that like simple metal complex itself, some molecules are very biologically active. You know, recently we just published last year, 2024 beginning, one paper in inorganic chemistry. We collaborated with biosciences or bioengineering department. There we have done anti-cancer activity. That wonderful. Vanadium chemistry, vanadium compounds are very good. So we did for that, and we have published paper in organic chemistry. Simple molecule give very good results. We were able to publish it. Okay, but these organic molecules we have never tried it. The reason is limitations. We have a limited facilities. Within that, see, we cannot put our hands all over. Okay,
Yes.
करते हैं ना, दो नाव पे चढ़ना, और आगे का तो आप लोग जानते हैं, ठीक है, तो वो वाली बात है. तो बेटर टू स्टिक विथ योर केमिस्ट्री वेयर यू कैन डू बेटर. Okay, so we have tried that. That's all.
Sir, if you have some molecules,
Mhm.
final molecules,
Uh-huh.
characterized, because it is much difficult to re-synthesize. So if you have and you permit me, I need some molecules because they are very much active for my purpose, because I'm working. So some
You send a student to the department. I will not come between you and your scholar and my scholar.
Yeah.
You can have a 50 compounds.
Yes, sir.
They must be having that.
Thank
I'm
you
very
very
sure.
So,
If not, they can prepare it.
okay,
Oh,
so we
yes.
can do further process.
Yeah,
Salim
of
sir,
course.
Salim sir is doing theoretical chemistry. I'm doing.
See, the
weight
thing is
chemistry.
what I said, that with the limitations what we have and also constraints work within that, you cannot expand too much. See, for expansion you need collaboration then, definitely, because you cannot have all facilities in that. The person who is bioorganic or bioorganic then he won't synthesize it because they are afraid of synthesizing. ये कहा बहुत सिंपल सर, नहीं नहीं नहीं, आप अगर आप दे सकते हैं तो ठीक है, मैं प्रिपेयर नहीं कर सकता. दिस इज द फैक्ट. Those people doing say anti-cancer or other activities, they need a molecule. They are looking for, आप दीजिए, हम नहीं देते हैं क्योंकि फिर वो स्टूडेंट हैज ए लिमिटेशंस. और माय ग्रुप, I set the parameters of 4 years. It should not go beyond that. Okay, so within that period you work day and night. As you don't work, I don't mind. We need a result, and my strategy is that when you leave, your all thesis should be published, and better to publish in a good journals. That's all, and you will see that you have some feeling. That's all.
Thank you, sir.
Okay.
So thank you very much, sir, for giving for delivering the very good and informative and wonderful lecture. Yes, please, Shahzadi, Doctor. Sir.
My question is, how does the choice of metal like nickel, palladium or vanadium affect the reactivity and performance in heterogeneous catalysis?
See, now when you say comparison, I cannot compare it because I told you that I'm an organic chemist and more known as a vanadium chemist. Worldwide, I'm very well known. If you talk about vanadium chemistry, people take my name. Yeah, I can do vanadium. So I have tried in the beginning, in the very beginning, I tried with copper, nickel, cobalt, everything. Then I was not very happy. Stick with one metal, do something, world should know in that area. Okay, I have tried vanadium, to some extent molybdenum and tungsten, not more than that. When you look at my record in last maybe 15 years, people ask me why you are not doing any reduction type of thing. I said, Baba, my catalyst doesn't go for the reduction, go for oxidation, aerial oxidation, use oxygen source, use like hydrogen peroxide, use other oxidant to go for that. I found it one way to move further, faster. That's all. Yeah.
Sir, morphology of the polymer affect the catalytic homogenization heterogeneity.
See, definitely. If you add within the morphology, that is called BET, surface area. Okay. When you do that, that gives you idea how much volume you have there where your catalyst approach to the metal center or not. Okay. Like in catalyst, when you talk about this polymer beads, they are very hard. When you put it in DMSO, this swelling occurs. Okay, when you swell, you have a pores available. I haven't shown any picture. I could show you. Pores can be seen through the morphology. Pores are available. They can enter right there quickly. If they can enter is easily reach to the metal center, it works better. So homogeneous. That's why the homogeneous catalysts are really good. The reason is, as soon you add into the solution, the metal center is easily available. Okay, but the only problem is that the what you call the recyclability, reusability, because it cannot be taken out from the solution. It is highly soluble in the reaction mixture. When you make it heterogeneous, there is certain condition. Whether your substrate is able to reach easily to the metal center. If it can reach easily, definitely that will work as a good catalyst. Simply. Okay? हाँ प्लीज प्लीज मुझे पता था आप एक क्वेश्चन पूछेंगे हाँ बताइए
As far as the catalytic action is concerned with the vanadium complexes, uh, have you seen any difference between the paramagnetic vanadium complex and the diamagnetic vanadium complex?
I think you had a curiosity of paramagnetic diamagnetic. I'll tell you that. See, these all reactions what I showed you, these are not like a reduction or anything. Everything is through oxidation, right? All reactions through oxidation. Now when you are doing oxidation, you are using oxidant, maybe simple oxygen source, maybe molecular oxygen, maybe other oxidant like S2O2 or TBHP, etc. So when you have a vanadium 4 like paramagnetic now, okay, for example, as soon you pass air, vanadium is very sensitive to oxygen. Vanadium 4 is very sensitive, though we think with one electron present in d orbital, vanadium 4 should be very stable, but it's not stable, highly unstable system. You know, sometimes what we have observed, I'm not showing you here the homogeneous chemistry. In a homogeneous system, we had vanadium 4 compound. In one case, not in all case, we just simply grinded it in a, using pasteller mode, and it oxidized to vanadium 5. While recording magnetic property, prepared it today, after 1 week record the compound, magnetic property become diamagnetic. Second day you prepare, you have a half of that one electron going down, oxidizing. Once you pass the vanadium 5 compound, I tell you now, disclose it here, homogeneous system. Whenever we prepare the vanadium 4 precursor and we prepare only vanadium 4 compound, and when you convert into vanadium 5, either you pass simply oxygen, एरियल, ये आपने वो देखा होगा ना, फिश पॉन्ड, ये जो घर में लगाते हैं, क्या बोलते हैं उसे, एक्वेरियम, उसमें ऑक्सीजन बबलर है मछलियों को देने के लिए, वही बबलर हम लोग वेनेडियम कंपाउंड को देने के लिए यूज करते हैं. सिंपल सिस्टम से. दिस इज क्रिएटिविटी. माय स्टूडेंट, वी आर स्ट्रगलिंग फॉर. एस्पिरेटर लगा के पास करते थे, ढेर सारा पानी गिरता था, बच्चे मार्केट में गए, बोले सर ये बहुत बढ़िया काम कर रहा है, इसी को ऑक्सीजन सोर्स के लिए यूज कर लेते हैं. इट वर्कड. when I started this chemistry, vanadium chemistry, I failed at several instances कि vanadium 4-5 में जा नहीं रहा. The first, it took me almost 4 to 5 months to understand how this will go vanadium 4 to vanadium 5. रात को एक दिन फ्राइडे नाइट छोड़ दिया, सैटरडे संडे कुछ नहीं कर पाए. मंडे में आया तो देखा कि सरफेस पे ना ऑक्सीडाइज हो रहा है. समझ में आ गया, एस्पिरेटर से ऑक्सीजन पास किया, धीरे धीरे सारा ग्रीन कंपाउंड रेड में कन्वर्ट हो गया. समझ में आएगा यही है. वो दैट क्लिक दैट डे. इट वाज 1998 एंड नाउ हाउ मेनी इयर्स, 27 इयर्स. वो ऑक्सीजन अब सोर्स बदल गया. वो मछली वाला जो है ना, वो आ गया यहाँ पे ऑक्सीजन पास करने के लिए. सो व्हाट इज हैपनिंग एक्चुअली टू योर क्वेश्चन, नाउ कमिंग बैक टू द 4, when you add oxygen or oxidant going to 5 immediately, okay, and is doing the catalytic reaction. In some cases they come back to vanadium 4. So vanadium 4 paramagnetic molecule is also equally active like your vanadium 5 diamagnetic. Okay, only thing is it may be little delay, because when you are adding oxidant, it is converting from the 4 to 5. That much time it may require. So you may have some stagnation period. Ultimately, it gives you the same catalytic property.
As far as the stability of this polymer is concerned, adenine material that is more stable.
No, not like that. I have shown you that butting for EPR. You want to go me back again? EPR, when you add H2O2 or oxidant, it is converting into 5, become flat, no EPR. When you add a substrate, oxygen is transferred and then it's coming back to 4. So stable, surprising to me also. To surprise, to collaborator also, how this is stable, but it's really stable. It's going to. Maybe the ligand system what we had taken. In other case, it is going to 5 and become 5 because you are using oxidant. So it's stable in 5, but still it can be characterized very stable. Recyclability is there, but 4 is going to 5. So what we have tried to remove ambiguity, and maybe reviewer like you is stable 4 or 5, confirm it. We try to prepare 5 only. Okay, safe way to do it. Any other question? We have published almost 100 papers in vanadium chemistry. 25 years continuous, and still, like this year and previous year we published paper in organic chemistry using vanadium chemistry. So I feel that still vanadium chemistry is going well after 27 years. We have still scope.
Thank you, sir.
Okay, thank you. Any other question? No question. Okay, thank you so much.
Now I would like to invite Professor Saif Ali Chaudhary and Salim Javed sir to facilitate our distinguished speaker as a token of respect. Please, sir.
भाई इस जगत में सर्वाइवल बहुत बड़ा काम है, ठीक है? अगर हम 20-22 साल से सर्वाइव कर रहे हैं तो कुछ तो कर ही रहे हैं।
सर इधर आ जाएंगे सर यहाँ जी।
इधर आइए, इधर पास से खींचिए तो पहले से खींचिए जैसे हम चार लोग पीछे वो भी आ जाए लास्ट स्लाइड वो भी आइए थोड़ा इधर हो जाते हैं, हमारी 2 फोटो आएगी। चलो आप प्लीज दो बंद हो जाएगा चलो बंद कर दो। Thank you sir. Thank you very much sir. It's my pleasure. Actually, past 25 years. जी जी आप आए। अभी कभी yes इसीलिए हम लोग छोड़ना नहीं याद रखते हैं, बहुत अच्छे रिलेशन जी जी बिल्कुल। पहले आपके
Good afternoon and welcome back. I welcome you all again to the second session of day 3, and we are privileged again to have Professor Maurya among us. And as you can see on this slide, he is going to talk about zeolite Y encapsulated heterogeneous metal complexes as sustainable systems for catalytic oxidations, a challenge for chemists and chemical engineers. So again, we are going to have a learning experience for another 1 hour. Sir, welcome. Welcome again, and it's over to you. Thank you.
Thank you, madam. anyway, अगर ये लेक्चर अच्छा नहीं होगा तो हमारा कोई कसूर नहीं है. हाँ, मैं बता देता हूँ पहले. ओके, ऑल राइट. हाँ, okay. Now his topic is very close to the previous topic but is slightly different, and you may find some slides even common because ultimately it's catalytic reactions, right? And of course again that will be almost similar kind of metals and oxidation reactions, right? So now the topic here, that zeolite Y encapsulated metal complexes basically, and of course that will be heterogeneous in nature. Now second, a challenge for chemist and chemical engineer is in question mark. Okay, the question mark is missing because he did not put the question mark. Okay, in the title, a question mark. There is really, is this topic is really challenging to chemists and chemical engineers or not? We will try to answer it. Okay, so to start with, again almost similar slide, catalysis. Okay, see the role of catalysis. When you look at there, almost more than 90% of petroleum refinery petrochemical process are catalyst based, and 90% of processes and 60% of products of the chemical industry are actually catalyst based when you look at that among heterogeneous. And 95% pollution control technologies and alternate fuel productions are governed by the heterogeneous catalyst. Means heterogeneous catalyst is dominating over homogeneous catalyst. The reason I mentioned the morning itself, the reason is because the recovery of the catalyst or the separation or the difficulty in separation of the catalyst from the reaction mixture. Okay, because of that, people started moving towards the heterogeneous side. There may not be that heterogeneous catalyst that good what homogeneous catalyst does, or that shows the catalytic activity. But even if a 10% catalytic activity is less, and if catalyst is recyclable, it can go to certain extent, certain cycles, then it's always better because you are ultimately not losing anything, you are gaining, though you are getting the less conversion or less oxidation, less active. That is fine. Okay, so see the there, this is given here in detail, that industrial catalyst heterogeneous these days approximately covering 80%, and homogeneous is about 17%. So you can see the ratio. Earlier, during the time of Ziegler and Natta, homogeneous catalysts were more popular because those days heterogeneous catalysts were not much known. In other words, I would say that. Okay, and now biocatalysis is coming up, and in the future, in near future, you will see that this figure, what is 3% here, it may dominate because this is very safe. Green kind of catalyst you can now name it, because these days people are talking about green everywhere. As soon you write something, even you title up your paper green, that people see through attention. Okay, because immediately some feeling comes in the mind, why green is written, let's look at that. Okay, so the green chemistry became an entirely different field because of this one. And also people are talking about too much pollution, too much poisoning, to the human being environments is coming up. So the heterogeneous catalysis and biocatalysis have a future, but whether the topic what I have chosen is really having future or not, we will look at that. The demand for catalysis, see, these days almost 4 to 5% is growing every year. It is growing up. Global catalysis market size, it is given here in 1991 data, sorry, 2019 data. All right, this is like 33.3 billion in 1990. See, 2019. Huge market is there. Okay, so and it is expected that in the Pacific area, Asia side, this is going to be more and more and more in near future. Okay, so catalyst contribution in the nation building, how it is contributing. Always look at the GDP. is covering 24% of that. It means they are having some future because of the heterogeneous nature that is important in general. Okay, we look at the all. I mentioned the previous slides. Only what we looked at: fertilizers, pharmaceuticals, or in talk in terms of fuel, energy, everything that is covering these days. Okay, so it means the heterogeneous catalyst has a future and it can dominate. It is dominating over the homogeneous catalyst because they are recycling in nature. They can do further. So in the morning, I talked about one of the process for say how to make a heterogeneous catalyst. Even if we have a homogeneous catalyst, if you can polymerize it, you can make it heterogeneous. What you need to do it, you make it insoluble in most of the solvent, okay, and then it can be used. So in that terms, coordination chemistry plays a very important role. Select the ligand in such a way that it can make a polymeric material, polymeric compounds, polymeric metal complex, not mononuclear. Go for polynuclear. Not even dinuclear, trinuclear, that may have some solubility issue. Okay, solubility means they may be soluble, but when you polymerize it, that can go very easily and you can make it heterogeneous in nature. That works on the basis, on the principle of the homogeneous itself, but because that is insoluble, reactivity, activity may be a bit slow, but it works. And we have tried it in the beginning when I started my career by polymerization of the metal complex. It worked, and catalytic activity is not bad. We can do that. Another process, that is immobilization. What I presented in the morning, I used organic polymer. These days, inorganic polymers are also very well known where the materials can be immobilized on the surface itself. You may be knowing some of them like MCM 41, SB. These are all like silicates, aluminum silicates, substituted aluminum silicates, and others. And they are porous materials working very well. They are polymeric materials. There can be homogeneous catalyst can be embedded through covalent bonding, through adsorption, but they are working very well. So that is one method. And the last method, what I mentioned here, that is almost similar to the number 3, but this is zeolite encapsulated. Okay, so let's talk about some zeolite first and then encapsulated one. Okay, zeolite. Most of you must have read now because this now you can find this one even the course of like 12th standard also. The definition is given there at least. What is a zeolite? It's a simply aluminum silicates in general when you talk about, but having some framework. And we look at their three-dimensional network of interconnected large spherical cavities known as super cages. They are called super cages. Okay. And when I look at the structure, may not be very clear here. I'll show you another slide. Okay. There you will see a good large cavity. Okay. So there the linked by opening defined by 12 oxygen rings. Okay. Structure provides a high surface area, specific pore size, making it valuable application like catalyst itself. So zeolite itself can act as a catalyst because aluminum is there, silicate is there, and it depends on what kind of zeolite we select. There may be some metal ions attached along with that. So that itself can act as a good catalyst, a heterogeneous catalyst. When make it metal complex encapsulated, then definitely that going to make a difference. Okay. So when you talk about that, see, hydrated aluminum silicates because it has a big void, lot of solvent like water molecules can be there, and that actually helps in finding out the pore size itself. You need evacuate all, remove it, and measure the pore size. That can give you very idea. Okay, definitely. And also this is three-dimensional network, contains channel or interconnected voids. The formula that is more important. See, M2 by N O ALO2 X SiO2 YS2O. YS2 Y may be more than 100 because it depends on the size of that cavity. Okay, and number of negative charge equal to wherever negative charge comes, mostly balanced by the aluminum. Whatever remaining, that is balanced by either hydrogen or any metal ions. Okay, that is the beauty here. X is generally are equal to greater than 2. Number of water molecules as mentioned gives the volume of the channel. Zeolites are both crystalline and porous type. I'll show you some structures, maybe that what is called that FESM. Okay, and beauty that when I mention here M2 by NO, okay, M can also be hydrogen, H plus ion can be simple hydrogen, and it can be any metal ion. And good part of this zeolite is that hydrogen ion can be replaced by metal ion and vice versa. Metal ion can also be replaced by hydrogen. When you take in the acid, proton takes up. When you take into the base, the metal ion takes up. Like sodium hydroxide, what I'm talking about. Sodium chloride, simply if you have a H zeolite, treat in the water with sodium chloride, it's a saturated solution. All outs, not all, but most of the hydrogen can be replaced by the Na plus, because the rest, whatever balance charge coming up, that is taken up by the sodium ion. And also sodium ion can be replaced with the metal ions, other metal ions, transistor metals, what we talk about, because that can enter easily into the what is called the cavity. Okay, so this exchangeable property of this hydrogen versus nitrogen, or sorry, sodium, or sodium versus other metal ions, that is a very good, you will find later. Okay, so this is good. Other thing is that homogeneous catalyst, mostly metal complexes. I mean, organic chemist talking about metal complexes may be considered as one of such interesting molecule which can be inserted into the cavity. Okay, and zeolite encapsulated complexes then can act as a catalyst. And benefit of this one is because you have a homogeneous catalyst, after insulating into the zeolite pore void, you are making it heterogeneous in nature. So beauty there is that if you have a little bit smaller size, then the cavity you can move around. It is attached to van der Waals forces, or the metal ion attached connected to the aluminum, or somewhere connected it, because you have exchange hydrogen ion for the M plus ion, and it can move around within the cavity of the zeolite. So there, enjoying both properties, homogeneous catalyst because it's metal ion, metal complex, and heterogeneous catalyst because it cannot come out of the cavity. So if I talk, or if I compare, in other words, around which say polymer supported catalyst, what I talk in the morning, and now in the afternoon, this material may be better than your other polymeric or materials supported on the polymer, because there it cannot, if it cannot come out of the cavity, there is no question of leaching from there unless that compound is decomposed. So under the condition when compound doesn't decompose, if catalytic activities are carried out, this should give you better catalytic activity, better performance than the material supported on the polymer. Okay, so that is the question. Okay, with this question we move on. This is the one. Now here picture is very clear. If you look at there, there are 1, 2, 3, 4. Can you see the four holes where material can enter into? All sides it can enter. You have a small pores on the outside and then big one inside. Like we have a ball, cut it from 4 different places, make a small hole, let the material enter it. Suppose you have a squeezable ball, okay, and it enters and then expanded. It cannot come out with any way unless you break it down. That is the beauty of this zeolite. Okay, and when you look at their side, some T is equal to silicon and aluminum, then you have oxygen and sodium. You will find that different places sodium ion is there. Why sodium ion? Because those hydrogen ion are replaced by the sodium ion. Sodium is called NaY zeolite. Sodium zeolite. Why? Why? There are different categories. Their name given depends on the cavity size. Okay, and the beauty here is that even aluminum can be replaced by other metal ions. Okay, under certain condition, or when you are making this, because this can be made in the lab. The very National Chemical Laboratory, they used to prepare in kilogram quantity, because there a long time project was there during 1990s working on zeolites. If you know the IPCL, Baroda, there lots of projects were given from there to NCL, and NCL returned it some good, you know, what is called catalyst, and and they used to use that like patented catalyst. Okay, so here all sodium ions can be replaced very easily with the other metal ions. As I mentioned in the beginning, that if you have a simple hydrogen ion, you treat with like mild sodium hydroxide, so all hydrogen can be replaced, or most of them can be replaced. And then if you have a little bit concentrated solution of any metal ion, simple distilled water, you dump your zeolite, you add metal salt, stir it maybe for 24 hours, you will find that most of the sodium ions are replaced by the metal ion. Okay, so there now you have a metal, like transient metal exchanged zeolite white. Now metal ion is available. So if ligand, organic ligand of course, can enter into the cavity, it can react easily with the metal ion, and then it can form a metal complex. So need is to make a device how the ligand can enter into the cavity, it can interact with the metal ion to form a metal complex, and if size is compatible, it cannot come out of the zeolite because inside cavity is bigger, sometimes as high as 12 to 13 angstrom, and the small that is having 4 to 5 angstrom only. It cannot come out of that. Okay, so how to make the metal complex? So there is one method called flexible ligand method. I'll discuss all one by one, maybe if possible. Template synthesis method, zeolite synthesis method, ion exchange method, absorption method. Okay, and as I mentioned here, that during 1990s, this was the project when the then Deputy Director Paul Ratnaswamy, I was also there in NCL for some time, okay, working as a pool officer. Then he called me one day, Moria, I have got one review article, very small review article was there. Just you read it, you are an organic chemist, and I think you can find something interesting in there. I read it. Then I discussed with him, sir, this is this is talking about, they are talking about metal complexes encapsulated in zeolite. And you know what was name was given? Sip in a bottle. Sip in a bottle. How, like you must have seen in the market when you are going to somewhere, really bottle and sip inside there. You will find it like market where you are going some picnic spot or other place. You will find that. How this sip is made inside the bottle, that was the question. The same thing here. That name says that sip in a bottle complex. Now, question or name letter came that metal complex encapsulated zeolite. That's all. Okay. So then I thought, how to do that? Is it possible? Then I read through. Then we actually able to understand that this is the way to move on. You first you have a NAY, then exchange it. You can have a material, whether you have metal exchange material, and this is the one this slide is shown here, like you have a CO2 plus ion. So not 100%, but 60, 70, some percentage metal ion can be inserted into the cavity, okay, of the zeolite, and then you have a solvent. Earlier what we started, that we are not able to understand very well, so we selected such a kind of ligand which are having a good melting point. Okay, melting point means a certain temperature it will melt and form a liquid. So have a excess amount of ligand, melt it, and you add your zeolite where you have a metal exchange zeolites available. So that used to enter into the cavity because ligand is flexible in nature, enter into the cavity, react slowly, then separate it, and then wash lot of solvent by stirring into the excess of solvent, and then remove all excess ligand. Okay, then later we realized that we can go by regular solvent, just take this material in any solvent, and where ligand is soluble. So when ligand is soluble, it have a flexibility in nature. It can enter into the cavity very well, and it can form a metal complex. So this was the idea that was generated during 90s. Okay, and then when you have this material solvent enter into the system and form metal complex, you can also visually see that when you filter it, if suppose you have a copper complex and it forms, like suppose you have a nickel complex, you know, nickel DMG complex, very pinkish in color, zeolite is white in color. So as soon metal complex forms, the color of the zeolite change. So you will have a pinkish color compound, you have bluish color compound, though the metal content along with the metal complexity or the total amount of metal complexity is very less. But the shade, you can immediately see that change. You will find that it has entered into, even after lot of extraction with the other solvent where ligand can be all washed out, this can be seen. Once the metal encapsulated complex is formed inside the cavity, there is a good possibility that all metal ions do not react with the ligand. Then, if metal ion itself is present, you know that metal ion can act as a catalyst itself. So we need to remove those metal ions. So what do you do that? Then reverse process. Treat with this sodium chloride solution for longer period. So slowly all metal ions can be exchanged with Na. So Na, metal complex zeolite, where sodium ion has to be there definitely all the time. Okay. So then you have a, say, the simple ligand was there when I talking about the melting point, melting of the ligand. So saline was the best because this could melt around 120 temperature very easily. So you can increase the temperature by say 140, and then it becomes a liquid state. It can enter into the cavity. Okay, so that was. But later the process was modified, and the Paul Ratna Swami and his group, because I left after 2 years, so he that initiation was by me. Then his group to his research scholars, they extended this one, and they prepared lot of compounds and then published paper and got the PhD thesis. Okay, so that was the initiative. So here now other method is there. That was the flexible ligand. But now the other method is that is called that absorption method. Adsorption method. It's not. It should be adsorption. Okay. So here first step is same. Now in second step, see, this is through when you have metal exchange solid materials, then pass different gases, like you know that carbonyl. In the morning you were talk, your topic was in IR different carbon monoxide adsorption. Okay, so there when you pass through like mixture of carbon monoxide and hydrogen, or sometimes carbon monoxide and water, like when you pass through, so if metal exchange zeolite is there, then carbonyl react with the metal ion and form metal carbonyls. Okay, this was that is called that adsorption method. Okay, so you have like different kinds of compound made there, like NiCO4, IR4, CO2, etc. All carbonyl compounds, because those carbonyl compound, if you go to the catalytic chemistry, you will find a lot of application of carbonyl compounds in different reactions. Okay, so these were the method evolved for the metal carbonyl preparations in encapsulating zeolite. And then the template method is there where you have a ligand separately, you have a metal ion exchange zeolite. Like if you look at the bottom structure is a macrocycle. Macrocycle cannot enter directly into the cavity because this is not flexible. Silent ligand, other ligands are flexible enter, they can enter into. So how to do that? Then you have to go for template method where like the first step we have a diamine compound, orthophylline diamine, taken to the solvent that will react with, because that still is a, like bidentate ligand, it can react with metal ion. Then if you add like diketone, it can enter also because it's a liquid phase. It can enter into and react with the NH group, NH2 group there, and can form a bond, double bond like azomethane group, and can form macrocyclic inside. So you are tailoring the formation of macrocyclic inside the cavity through the template method, and you can prepare it. Now this is again example of the template method where see this is designed. You have almost like a saline type ligand. You know saline means, I'll show you structure. Ethylene diamine and salicylic interaction that becomes a ligand which is having two azomethane group, salicylic group this side and ethylene diamine connected through azo group. Okay, so this can be prepared, and when you have a that is called the zeolite synthesis method, then there like thylocyanine porphyrin molecules are encapsulated with the zeolite. What they have done is they have a starting precursor silica, alumina and sodalite, and then fused together along with the precursor of the porphyrin or thylocyanine. There it mixed and heated at high temperature so that they and in the solvent are others, so that the zeolite formation occurs at the same time the thylocyanine formation both together, because you have all fragmented. Okay, so when it comes all together it will form their thylocyanine and metal complex inside the cavity only. Okay, and then you wash out, remove everything, and then you have a encapsulated metal complex. We have applied the flexible ligand method to prepare such metal complexes. Okay, and here when you look at there, the strategy is same. There is no change for that. Strategy is same. So we have prepared that in first step that compound. Now the Y represents the zeolite. Basically here we cannot make it all that way. And then by sodium chloride exchange, all excess metal ion has gone out and OH group is replaced by the chloride ion. So this metal complex has formed there. Okay, and the same one like when you have vanadium compound, like vanadium precursor, vanadium salt, treat with you have a VOI in cap that like vanadium oxide exchange zeolite, and then you have a ligand. देखिए methanol reflux it for say 24 hours in the presence of oxygen. You will ask the question why oxygen is there. Now, sir, your question vanadium 4 and vanadium 5. Okay, paramagnetic diamagnetic, because characterization of diamagnetic becomes a little easier. So we have used air. So vanadium 4 oxidized to vanadium 5 and the ligand attaches there, so that will form double bond, V double bond O, V double bond O, two oxo groups are attached there, and it can be seen like this way, vanadium complex encapsulated with the zeolite. Characterization becomes a little easy because then two cis bands can be seen very easily. Okay, in the IR. Now, how to characterize? That's the question. Characterization, when you have ICP-MS, you can find the metal content. Okay, through FESEM, you can find morphology and also you can find the metal content. Through TGA, you cannot find metal content here. The reason is because you have alumina, you have a silica. Silica is highly stable. When you heat it, this will not further decompose, right? So metal content determination through TGA it's not possible here. The only possible way is through ICP-MS. And one more, what is that? Metal content, other method for the metal content estimation. Okay, so we can see that once metal content is there, still we cannot say that this is encapsulated. Then you have to determine the nitrogen. Nitrogen, like any method, it can be used. So when we have a metal nitrogen, because most of the ligands are having the metal nitrogen content and metal content. So once you have a metal and nitrogen content available, you can approximate the formula of the compound. Okay, TJ, see TJ is giving 7% or 4% like loss up to 100, up to 800 is how much loss is there between 250 and 800, 10%. Because neither alumina nor zeolite is going to decompose it. So, but that gives you feeling that part of the in the beginning when you heat it say 150 to 250 degree, say between 150 to 250, below 125 there may be some like moisture and other content can come out from the cavity of the zeolite. Still lot of water molecules are trapped inside, they cannot come out, so unless you heat it at higher temperature. So because of that in the beginning what is and water molecule is coming out. After that, definitely after 250 only, that will come due to decomposition of the metal complex. All right. So that can give you idea about the decomposition of ligand, and whatever the percent content you are getting, that is coming due to ligand present in the cavity. If that is perfectly washed and all non-reacted ligands or free ligands are removed from the mixture. Oops. Now, see, characterization. Scanning electron micro. Whenever you do this, when you have a only metal ion exchange, you will find the surface not crystalline in nature because part of the metal ions are present there. Okay, maybe on the surface, inside the surface, you will find not very good one. But once the metal complex has formed and it is washed very nicely, thoroughly, to remove any metal content or metal and metal complex from the surface, you will see that the sharpness in the crystalline nature of that zeolite. That gives feeling that the crystallinity of the zeolite is still maintained after encapsulation of the metal complex. Only that much information your morphology can give. If you have a ACM attached, EDS attached, that can also give some idea, but that does not give correct idea. The reason is because in the zeolite encapsulated metal complex, your metal content is inside of the cavity. Okay, if it happens that when a pore is void is available, hole is available, through that if instant light goes there, can give you some idea. So some metal content definitely you will see, but not the 100%. Okay, so that is the only problem, but still you can see that you can have idea. Other thing is that electronic spectroscopy, that is helpful to sometimes, but again, how to record the electronic spectra? The one what I told in the morning, that grind it in the nozzle nicely, make it very like suspension, like emulsion type, make attach what is called the paste in the cuvette in one, and other one make it nozzle reference. You should be able to record it, and sometimes we get good information out of that. So if you have a say charge transfer band, you should be able to see that. If you have a like band due to organic moieties transition, like pi n to pi and pi to pi transition, you should be able to see that. And sometimes if you have a unpaired electrons, then DD bands you can also see that. It's possible, very good possible. Okay, so that can be characterized. So all the see IR is listed here and UV visible listed. You should be able to see that. And then characterization by powder XRD. People have used powder XRD very frequently to characterize it, but frankly speaking, this does not give any information related to metal encapsulated complex. What is information that XRD gives about the crystallinity of the zeolite? Whether you have a NAI is perfectly crystalline, all peaks are coming due to, because you know that crystallinity means peaks are sharper, right? So from first to second to third, what you get it that even after exchange of the metal ion, crystallinity is maintained. After encapsulation of metal complex, your in crystallinity is maintained. You will see that there is no change in peaks. 1, 2, 3. I do not see any. Now, the question comes: what about the metal complex? Do you get any peak due to metal ion? Very rarely, small, tiny peaks. Sometimes, if you have a considerably good amount of metal complex encapsulated in certain number of void or the hole, then you should be able to see. Otherwise, you won't be able to see that. But at least gives idea that crystallinity is maintained even after exchange with the metal ion and exchange with the metal ion interacted with the ligand. Okay. Anyway, that is good enough to see that. Now, these are some characterization. We were see when we started chemistry at IIT Roorkee, there was no facility except FPSM and powder. That's all. Nowadays, facilities are available. I wish I could do some chemistry, but I haven't done that. So when we started, after doing all characterization, we tried it. Let's try simple catalytic reaction, very simplest one. This was before I started the polymeric materials. Okay, so this one is simple, very, see, phenol. Phenol is there, the oxidation of phenol, which the phenol, polyphenol, etc. That can be oxidized very easily. That can give you a good materials itself. So, see, phenol being ortho and ortho and para directing group, the product form will be, see, ortho position and para position, right? So, with this one, we started it and we tried to do the, because there was no GC available when we had to rush to the chemical engineering, and chemical engineering has one GC where you have to note down the reading all the time. Yes, manually, when you're running it, run and then note down the reading. Those days in 2002, 2003, etc. Okay, but at least we are able to see that some converging is going on. How much it was difficult, very difficult, maybe plus minus 5%, but gave some these catalysts we use. This is the like a silent type of ligand, the second one copper compound. Okay, that you see that it should be ethylene diamine, it is propylene diamine. That is the one. Okay, so how to see that? That was first thing to see the optimization condition for that, because we are using oxidant. So how much oxidant is required to get the best result? How much of catalyst is required to give the best result? Okay, so and if we are doing the reaction in solvent, how much temperature is required? So all optimization has been done one by one, and then after optimized condition, we have, say, this four different, this is related to S2O2 concentration. So you will see that some best result coming at certain condition. Then we have amount of catalyst, effect of temperature. So when you look at all and combine all these things to the optimization condition, then this is the one for the phenol oxidation for the 50 millimole. 50 millimole is too much amount, but we started with that. And S2O2 you require almost like 1:3 ratio, catalyst 25 milligram, temperature 80 degree. Minimum solvent is required to do this reaction. And look at there here. When you have a zeolite encapsulated, when we have a simple metal complex, when you compare it, zeolite encapsulated is giving best result. Though little bit more time is required, but it's okay. But catalytic activity is really better. But when you talk about in terms of the real good, the result is really good, it's not, because conversion is going maximum to 40 to 45% in any case. But it's better. Some results are coming. So those days we started with, and then this is the data, based on the selectivity. Of course, again, that we used to note down the what is called that area under peak. We used to note it down by hand, everything. Okay, so that data anyway is giving a good result. At least we are able to do that. So 40% conversion of the phenol is there, and with all cut collar hydroquinone formation. Okay, then we study the another reaction, which is the styrene. Styrene gave us 5 different products. What we expected that styrene should give styrene oxide, epoxide, best, not other products, but definitely we are not able to optimize to get maximum product like styrene oxide. Not, it was not possible. The reason is because oxidant ultimately oxidizing styrene epoxide to the other product. Okay, but it worked, and we were able to find out all different 5 products. By that time, during 2007, we got one GC in the instrumentation center. So we are a little bit better in position of that one, and we are able to do that. So this is for the another one. See, another catalyst. So optimization, now you are familiar with how to do that. Okay, and for the styrene oxide, styrene, this is the optimization condition, and in that case you will find that S2O2 we are using 1:3. The conversion is very good. It is going almost like 93-94%. But again, since we have a 3 times hydrogen peroxide, this is further oxidizing styrene to the other products. Okay, but conversion is very good. When you compare it, then you will see that the zeolite one is working really good, and within copper and vanadium, vanadium is giving good result. Okay, so vanadium acting as a better catalyst. However, when you compare within zeolite and non-zeolite, then there you find a big difference in their catalytic potentials. This is the data. You see that as high as 97%, copper is giving only 56, 57%. And when you see the styrene oxide, not, I mean, very pleasant result for the styrene oxide. The reason is because it's converting into other product. What is maximum is coming like phenyl diphenyl ethanol, or even going to benzoic acid. Benzaldehyde is maximum, so that is expected. Okay, so why it is going to the benzaldehyde more? This is one of the reason we gave during that period, that is styrene is going to epoxide. But since you have excess of hydrogen peroxide, it is further reacting with opening that ring that is known to open the ring, and then breaking it down, giving the benzaldehyde and the maximum yield. Now, the reaction what I talked in the morning. So we wanted to see whether this is working with this condition also. So we have taken sulfide, and we are able to convert it at even room temperature. See, optimized condition already given here. Okay, and then for the 5 millimole of the substrate, S2O2 require only 5 millimole, at least very less amount. Room temperature in acetonitrile, this is giving very good result. Okay, conversion more than 90%, very good result, and giving sulfoxide in very good yield, which is expected one, but if desired one is should get only sulfoxide, but some cases giving some percentage of sulfone. When you do without any catalyst in the presence of oxidant, then you will see that the result is very different. It means our catalysts are becoming more selective towards the sulfoxide, not the sulfone. So we are getting good amount of at least sulfoxide. Now, to propose the mechanism, this is one of the important part, that you take the help of the homogeneous catalyst. Okay, and when you titrate this regarding the UV visible spectra of the compound at different concentration of H2O2. Okay, so what do you see that when you add dropwise the solution of methanolic solution of H2O2 to the solution of metal complex, see the spectral changes, and during spectral changes you find at least 2 to 3 isosbestic point, and that suggests that the vanadium compound VO2 is converting into peroxide species. We could also record the EPR, not EPR, record the 15 vanadium NMR, but here the material is not much suitable for 15 vanadium NMR. So, restricted with only this UV visible spectroscopy, but the isosbestic point is very helpful in concluding that the dioxide species is converting into oxoperoxide species, and then oxoperoxide definitely the oxide of the oxygen of the oxoperoxide is transferring oxygen to the sulfide, converting into sulfoxide and sulfone. So that way we can, similarly in copper complex, not very encouraging result, but still you could see there the spectral changes here, but no isosbestic point in this case, because copper peroxo formation is not straightforward. Okay, there peroxo is mostly known there, they have a formation of peroxo through dinuclear compound. Okay, like two species coming together and forming, so you will not get very good or encouraging result that good, but still some spectral changes can be seen there. So particularly for the vanadium, this is proposed one, and that we also showed this slide to the previous lecture, but this is the best way to go it, because here peroxo formation is clearly seen, and so the reaction mechanism can be proposed. Now, the question is recyclability. This compound or these catalysts are very good recyclable. Okay, the reason is because, and that recyclable under the reaction condition, that is important. When you heat excess, definitely that compound has to decompose. So under reaction condition means when you have 80-degree, 100-degree temperature for the catalytic reactions, during in the solvent, compound is not decomposing at all because this is entrapped into the cavity. It is just moving in the cavity. It can move it, it can change the position, but it cannot come out of that. When it cannot come out of that, recyclability becomes very easy. And also to check it whether this is heterogeneous, the reaction is heterogeneous or homogeneous in nature. May some ask question may come that maybe the catalyst homogeneous coming out of the cavity into the solution and acting as a catalyst means part of the leaching occurs. That's the question. So to answer it, we have tried to solve it that you take the zeolite encapsulated complex into the solvent where you are doing the reaction, and after reaction, okay, you just remove the product, add more solvent there, and right there, sorry, filter it, we have, keep the catalyst out. Now if leaching has occurred, if you add a substrate and oxidant, more reactions should, more reactions should occur, but there is no further reaction after adding extra solvent, extra substrate and oxidant. The reaction is not moving. The percentage of the conversion remain the same, means there is no leaching of metal complex during the catalytic activity. So that is a good part, means the catalyst is recyclable. Other way, we have also done that. Separate the product from the reaction mixture, wash the zeolite insulated complex with acetonitrile, dry at 120 degree, and do the further reaction. Taking the same amount is giving the same almost same product, same conversion. It means catalyst is very stable and not reacting it. Okay. So we have moved further. So now we have prepared, see, these different kinds of cell and type of ligand with now the orthophyllin damage replaced by the cyclohexylamine. Reaction is same way. So characterization, you will see the metal percent we have done it, and the surface area, because it's not done by IIT, somewhere else it was carried out. Okay, some data were obtained, so just mention here. And then see the TG here, you will see that going from 110 like 100% OT up to 80%, not going beyond that. It's so stable, means partly decomposition has occurred in 2-3 different places. See, in the beginning, some water molecule, then up to 350, all water molecules what were trapped, and then at the end when it's coming between 350 to 600, that is only due to the decomposition of the metal complex. So that could give idea. Okay, so 3 different decomposition temperatures are seen there. Now same story for this one, you will find almost similar. Even if you take one and put it again in the separate another paper, no one would be able to see that. Only the expert can see that the same data, same what is called that is given or not. So better to record it. We should not cheat it. Okay. So that way it is done. Then UV will use spectroscopy, that gives very good information. Okay. We are able to see the band due to, because this is shown by copper compound, this is shown by vanadium compound. So the charge transfer transition can be seen very nicely. Only thing is you have to record in the suspension or the mole, paste it and view it. You can record it. So that's a good part. We could see that. Then catalytic activity are done here again, and the conditions are fixed in the particular reaction, and then here result is better, but the conversion, when you look at their distribution of products are almost same, not much difference. Okay, but again when you compare with the other copper and vanadium encapsulation is always giving better result. Now the question comes, that's why I love vanadium as not. Not definitely not due to this chemistry. Okay, but it's giving good result. So at least we are happy that this is chemistry is good. Then the regular cyclooctane, cyclohexane. This is the best way to check it whether your catalyst is active for the oxidation reactions. Okay, whenever people do that, people start with either cyclooctane or cyclohexane to see if your catalyst is active for the oxidation. This is the best way, like a model reaction to carry it out. We have also carried out it, but again, the reaction condition has to be optimized. Okay, and under optimized condition, you are giving four different products. Epoxide, you have a cyclohexanol, cyclohexanone, and then you have a 1,2-diol. Product distribution, this is under optimized condition. You see that vanadium on the top, encapsulated one, and the different products. Conversion is very good. Catalysts are working very good, recyclable, and only problem is with the, we are always worried about the epoxide. Okay, we did not know how to control it in the beginning. That is fact. Imandari say. But later we have done it, but we observed that if the reaction is carried out under basic condition, because acidity of the zeolite is the major factor to control such a reaction in terms of the product. When you make it slightly basic, you can control the formation of epoxide and you can increase the conversion of epoxide. Sometimes when you change the ligand, that also works. I'll show you that. Now we have a cyclohexane. You can do that oxidation easily. Conversion is a bit less, but under optimized condition, you will see that this is going to give you the product. Low conversion is not that good, like we have taken with this vanadium compound or the copper compound. With cyclohexane oxidation not an easy job. Okay. Now, see some more compounds we have tried one by one and tried to do all catalytic cyclohexane oxidation, epoxidation, sulfide oxidation, etc. So I won't spend time much here, and then we move to certain others. See, similar product, not much, no much change. Okay, but here you will find something different. When we have this ligand, that is called, when you have taken orthohydroxybenzyl condensed with acetaldehyde and making catalyst vanadium and copper, when doing this epoxidation here with the styrene, and here we have taken TBHP, tertiary butyl hydroperoxide. See the difference. Here we have 6.8 to 15% highest and sometimes even a 0 for the styrene epoxide. But in case of this one, when you take TBHP, possibly this is mild oxidizing agent than the H2O2. And when you have a styrene epoxide form, it is not going too much to the other product. So the here you can see that the epoxide is in much better yield. Okay, but as I mentioned that if you do the basic reaction, it is not done in this case. In other case, we have done the polymeric supported materials. It works better and give you better result. Okay, so in continuation, we have prepared some other ligands. And see there some vanadium compounds, some either copper compounds are shown. Vanadium compounds have also been prepared, and then after characterization these compounds, here we have tried to do EDX now available. Okay, and EDX you will see that one copper peak can be seen there, a small peak is there, so that gives the idea. But as I mentioned that you cannot see too much. Sometimes when you are lucky, you will see the small peak, but not like, because it's inside encapsulated, so you cannot see really well. But that gives some idea. But EPR spectroscopy is very helpful, not the krypton vanadium like other case I talked about. EPR is very helpful. After comparison with the homogeneous catalyst with the heterogeneous catalyst, you can get idea. You may not get those sharp peaks, but the major peak can be obtained, and you can calculate if you are lucky to get it first, and then calculation, if you know, you can calculate it. So all parameters are almost same like in homogeneous. Also you can find in the heterogeneous catalyst with slightly difference. UV visual spectroscopy is very helpful in characterizing that. The charge transfer band can be seen in case of the metal complex as well as in zeolite encapsulated. Now here all reactions are done again with this system, and you will see that now epoxide, even after changing the regular ligand to that one, epoxide is not very encouraging. We are getting mostly the benzaldehyde. And the reason is that because epoxide in the presence of H2O2 is breaking down the epoxy bond and converting into the benzaldehyde and of course the benzoic acid, etc. Okay, with manganese, just to see it if the metal change helping. So we have done some reaction with the benzoin, and the major product is actually dimethyl acetyl. After breaking the bond between the benzyl is 30%, benzoic acid 10%, and dimethyl acetyl is the 10%, almost 60%. But conversion is good. That is at least we can say that. So this can be done, and benzyl is not the bad product and not bad in yield, and this is useful in other organic reactions. All characterizations are shown here, and here you will see very clearly that even in encapsulated recording these electronic spectrum in usual, all DD bands even can be seen, though it is not much expected for the manganese compound because this is what is called that it's been forbidden. But due to change in symmetry or broken in the symmetry, if you know the basic, you should be able to see the DD band, and of course charge transfer band can be seen. So it is seen here. So it means the symmetry has broken down and you are getting some results. Okay, and also in case of vanadium it is very clear to see that. Okay, now as I mentioned that H2O2 titration, you will see that H2O2 titration very clearly seen that one isosbestic point at that particular point, and that isosbestic point is clearly indication that this even VO compound, even in this silent type ligand using pyridoxal as an side bond, it is giving almost similar result and converting into that. Now here, this is to give the reaction mechanism, we have used the homogeneous complex by stirring the 51 vanadium NMR. Okay. Now this is vanadium 4 compound. 15-1 NMR inactive. NMR inactive in general. So in the beginning, what is recorded after keeping the sample in solution for say several hours, so that oxygen has entered into it and converted into vanadium 5. So the peaks here, 2 peaks are seen, and also possibility that it is oxidizing, as well as since this is done in DMSO, so partly DMSO can coordinate to the metal center. So partly DMSO coordinated and the pure metal. So 2 peaks are seen there. When you further add H2O2, the peaks are better and better. And then also another peak you can see that is going due to the formation of the peroxo compound. Okay. Then move further. More peroxo species formed, and then you add what is that? Where is there? There is one peak that is where it is added the substrate. Substrate reacts with, okay, the top peak you will find that is after 30 equivalent, one peak is last one equivalent, that methyl phenyl sulfide. Okay, so immediately that peak due to peroxo has gone. That gives a clear indication that the peroxo is transferring oxygen to this one. So alternate way you can find out to give the reaction mechanism. This is theoretically predicted through theory DFT calculation, where it is possibility of the 51 vanadium NMR. You can see that, and it is predicted that the same way monoxo is going to dioxo, vanadium 4 to vanadium 5, then 5 is going to the peroxo, and then peroxo, when you add methyl phenyl sulfide, like when you have a excess peroxo, it can go to the metal free, ligand free metal complex, and can go back when you add sulfide, it can go to the peroxo. And if not excess of hydrogen peroxide, then it can convert back to the dioxo. So mechanism can be given. Okay. EPR for vanadium 4, that is helpful. So we have EPR for the compound, have a H2O2. Then after having added the methyl phenyl sulfide, or you see that the EPR is coming back. So if compound is not exposed to oxygen, when it remains in plus 4 oxidation state, and if you do the H2O2 calculated amount and have added hydrogen, of course, the methyl phenyl sulfide, you should be able to add the conversion going back to vanadium 4 compound, not vanadium 5. Only thing is you have to have a small amount of H2O2 added, then you should be able to see that such kind of changes. Okay. So this is one also, that is manganese compound. Quickly I'll show that. Okay. And this reaction we have done that. And remember that in previous chemistry I told you about the oxidative bromination of salicylic. Oxidative bromination of salicylic in KBr. So here with the manganese compound, manganese analogs can work very well for haloperoxidase model. Manganese, molybdenum, tungsten, these are the metal ions which works very well or go along with the haloperoxidase activity. So we have tried with the bromination of the styrene. And in this case, we observed the formation of 3 products. One dibromo, one of monobromo with hydroxyl group, the other is like diol. Okay. And if you look at that, first the optimization, obtain the optimized reaction condition and do the bromination. Fantastic reaction. Haloperoxidase model reaction can be tried with this one and giving a good result. Okay. And again, to give the reaction mechanism or to propose the reaction mechanism, this is one of the way to see that. Do the add the H2O2, then add the KBr, and at the substrate you will see the changes. Okay, that is the best way to go for any catalytic reaction procedure. Okay, so far what I told you that these catalysts are so good, but earlier due to restriction, or you can say that with the non-availability of a lot of instruments at our place, we restricted with certain reactions, but we observed definitely some good results. But what I also observed in the literature during the 1990s up to 2010, people were inclined towards the discovery of the heterogeneous catalyst through the zeolites. After that, not much chemistry you will find in the literature. But suddenly, last few years, particularly I'm talking about metal complex in zeolites, chemistry again is started. Okay. And this paper just see in organic chemistry is 2019. This paper by Witz Pilani. Wonderful paper. When you go through that, they have prepared the palladium compound. I was discussing morning palladium compound. Okay. So they have prepared palladium compound. Look at the ligand what they have used. Almost same ligand what we have used earlier. Okay. But what they have done, instead of orthophilindiamine, they have taken metaphilindiamine 1,3 and vanadium compound. They have studied the what is called the effect of the substituents in the cavity, and then what the chemistry can be done, Heck coupling reaction. Okay, I'll show you. So see now better instrument, and look at the crystallinity of these materials. Perfect. Other one where you have a metal complex on the surface, also on the surface metal ions. Here perfect neat crystallinity can be seen. And then, well, this is facility is available. BET, Southern, you can see that. Okay. Everything now because facilities are available. Now XPS can be applied in this case also because you have a metal center. So all due to nitrogen, due to seed development, everything you can see here, and metal content also you can see that. And then the reaction. Heck coupling reaction, well known reaction for the organic chemist when they start with. Or the palladium chemistry, when you have Heck coupling reaction, is most popular reaction. If you have a palladium catalyst, 90% papers you will see that Heck coupling reaction, different substrates, that's all. Okay, so they have done Heck coupling reaction, and this, look at this recyclability, 5 times they have done it, and perfect. So good paper, good study, good journal, right? Another one, same group, because now facilities are available, all right? Heck coupling reaction, palladium Heck coupling reaction. You know, if I wish I could do now chemistry start again, the Juliet encapsulated, I have lot of ideas, I can do that. I've shown in the last few transparencies in my polymer supported materials where we have done multi-component reaction. It is going to work because all substrate can enter into the cavity, interact with the metal center, and still can pass through that because those molecules are not bigger molecules, can come out of the cavity, okay, easily. Here, one of the important reaction related to pollution, carbon dioxide capturing. This project is going at very large scale. Now papers are coming, a lot of papers are coming on this one. Okay, theoretical study, sir, theoretical study is also coming. Okay, yeah, that's why I put theoretical study. Also the experimental, because CO2 capture, cycloaddition to the styrene epoxide, etc. All epoxides, these are coming like a hot topic. Another one journal is coming up, CO2, Journal of CO2, Journal of CO2. Separate journal is coming devoted to this chemistry, and the Juliet encapsulated complexes are working very good. They have driven it this mechanism. Yesterday only I reviewed one paper called the New Journal of Chemistry. It's coming only carbon dioxide cycloaddition reactions. It's coming up very good. Same group, see inorganic chemistry frontier. What is this? Again, the same group, and now here they have replaced palladium with the nickel. Same, right? Nickel, palladium, platinum. What is chemistry? Now I don't need to say that. Okay, Heck coupling reaction. Just I brought it to just show you that now interest is growing in this chemistry. Okay, and this, what is called that? Another group, this group. If you look at there, we have prepared the same compound 20 years back. 2004-5, they have used the same complex, same metal ions, same ligand, and published paper here. And what is oxidation they have done? Same reaction they have done. It's just like they have quoted our paper also, but repeated the whole thing. Just copy paste kiya. Oops. Okay. So reaction is coming up. Benzyl alcohol. Just to show you, the molecular catalysis paper came. All right. And this paper came just ACH only last year. So what you see that now the interest in this chemistry is increasing these days. That's what I brought these things here. Okay. So now question comes here. Whether Juliet encapsulated complexes serves as a sustainable catalyst? Answer is yes, of course, yes. I wish I could do this chemistry, I could start it. But now my days are over, your days are coming up. Okay? Because you are, if I talk about myself, this is third generation. Okay? Third generation is always better than the first one and also better than the second one. Okay? You can think better. Because these catalysts may meet the industrial demand of recyclability for continuous operation. Definitely is going to work better, and they have done 5 cycles. People have done sometimes 10 cycles, 15 cycles, where facilities are available. We are limited to, students are limited to PhD degree. Okay, IIP people, Dehradun, they do 30-40 cycles to show that, because they have to sell the product in the market. So they do that much cycles and so that catalyst is working very well. Okay, part of the people earlier, II people, they have done zeolites. They have stopped it because this government order what they have to do that. Okay, so but the field need to be explored because not many reactions are known in this area. You can extend it because you have heard the lecture. Now you can go through the literature. Characterization is not very difficult these days. Very, I mean, set characterizations are there. All facilities are available. Now people can do it. And all chemistry what can be done with the regular homogeneous catalyst, all chemistry can be done with this heterogeneous catalyst. Okay. I dropped this idea because limited facilities were there. And then when we picked up the polymer supported students, see students they want degree faster. They wants to stay here longer period of time and want a degree without doing something. Fellowship is very important. All right. So I think thank you so much. I have come to an end. Okay. The same slide repeating. Thank you so much. Any question? You can ask how to start. How to start geolite chemistry? I can answer it. How to start vanadium chemistry? I can also answer. Yes, of course. Yes.
You have proved that professor cannot be retired.
Yes.
In overall lecture I have seen. Some queries I have. In several conversion, you have used H2O2. Why not other peroxide, organic peroxide like
I have used 1 plus TBHP. I have shown you TBHP. TBHP, tertiary butyl hydroperoxide. See, you can also use oxygen. You can also use oxygen. Oxygen is a slow process because if you use atmospheric, this is going to take a long time. And the other problem is that, see, people have done that. What you are talking about, people have done this. The other way where they have a continuous flow reactor with oxygen, you can be entered into, like you have a like a block reactor, okay, and in the pipe you have put the catalyst, all right, and then you put the oxidant, you put the other materials going into reacting on the surface and giving the product. It is there. See, working in the lab, you have certain restrictions. We cannot use oxygen as a source. The reason is because control. Maximum you can use balloon. Okay. We tried. Once I thought, let's have a, pressure reactor. Pressure reactor where you have a what is called that reaction flask, stainless steel flask. You have all you can autoclave. The other way to say that, the pressure reactor that is called autoclave, where you can use continuous flow process. Autoclave, you can increase the pressure, you can do the reaction. Okay, with the help of NCL in the beginning, I tried it, but how long you can have help from others? You have to be independent, right? All the time when you grow, when you have comes to the promotion, people appreciate in the beginning. When it comes to the promotion, you are taking help from NCL. What is your contribution? They are contributing more, you are contributing less. I also ask the same question because I'll be sitting other side of the table, right? The same thing it comes. No, this is reality. This is reality of the world. Hey bhai, recording बंद कर दो, हो गया. Okay, this is a reality of the world. Okay, so you